Now, the subject today, as we know, is about this cloud. And to establish this, I need to say a few words about me and about the things that I have gone about in looking at it and how I approached it. Now, to approach something like this, first of all, the cloud, which we have the photo up here and has been sitting here for many years. There's a reason why we put that cloud up there, and it's because of the scriptures that we just read. But it's also connected with an event which Brother Branham had seen by vision months before and had detailed things that would happen. And when this cloud appeared, the eyes of the world was instantly attentive to it. The cloud was first reported to Dr. McDonald on the day that it appeared. Dr. McDonald lives in Tucson. And when the cloud appeared, somebody called him, said, "Look outside." He goes out and sees the cloud. He sees it way, way above. He shouldn't be able to see a cloud over Flagstaff if you're in Tucson. So it got his attention. He is a professor of atmospheric physics at the University of Arizona at Tucson. And being a professor of atmospheric physics, he's very interested in clouds and how they form, and this one was unusual. This one was something he had never seen before. And in fact, he reported that no one had ever seen a cloud like this before. This was something that in recorded history had never occurred. And it's also something that in recorded history has not recurred. It's a one-off event. It happened once. And it happened associated by the prophet's message. This cloud was associated with the events which God was doing at that time in history. Now, people have said, what caused this cloud? He was very interested in what caused it, and he offered a bunch of explanations. Among them, he's the one who first suggested that this cloud could possibly be due to that rocket that was fired off at Vandenberg Air Force Base 3.5 hours before. But in his scientific integrity, he did not say that that was the cause. He said he couldn't figure out how it would be, but if it were, then there's a lot of other things we need to investigate. And so the man was very honest. I appreciate his integrity, for one, because as a scientist, if you are in science, and those of you listening who are scientists or engineers or have done engineering work or have done root cause work, then you know that cause and effect has to be something you nail down very tightly. There's an event, there's a chain of circumstances which is logically connected by physical reality, and then there's a cause to that event. So there's a cause, a chain of circumstances, and then an event. And you can't break that. If there is a break in there, you're not allowed to say, oh, and then magic occurs, and therefore this happened. You're not allowed to say that. But in essence, people who haven't made the connection between the event or the cause of that cloud and what that cloud, when it appeared, if you can't make that physical connection, then you can't say you have root cause. And it's just that simple. So we're going to look at what could possibly cause the cloud to form. How do clouds form? How many of you, when you came in this morning, you looked up the sky and you saw the clouds? And some of you did. Okay, what kind of clouds were they? What do they call them? You know, high school, you learn meteorology. There's a few terms you learn. Those are cirrus clouds. Cirrus clouds, high in the sky. How high were the cirrus clouds? Could you tell? No way you can tell. The reason you can't tell is because clouds are something, they're fractal in nature. What does that mean? Well, fractal means it's self-similar. That is, no matter what distance you look at it, it looks about the same. And so if you're looking at clouds or looking at something and you just look up at the sky, you really can't tell how high it is or how far away it is. And so it was with this cloud. This cloud, when you look at it, you think, oh, well, there's a cloud. How close is it? If you didn't have some objective way of measuring it, you would never know how high the cloud was. Now, the other week, Brother Josh and I were looking at clouds. I don't know why we're looking at clouds, but we were looking up at the clouds. And so I said, Brother Josh, you see those cirrus clouds up there? Yep. I said, you notice the contrail of the jet flying amongst those cirrus clouds. Well, there's a contrail that forms out behind the jet, and it kept getting bigger and bigger and bigger and bigger and bigger. Well, all of the moisture that you saw in that contrail didn't come from the jet. That was moisture that was already in the air. What the jet provided was condensation nuclei that allowed a cloud to form around the tail end of the exhaust of the jet. And so the cloud keeps getting bigger and bigger because the moisture's already there. Now, there was another jet that was higher, and you could tell it was higher because you could see he was above the cloud. There was no contrail at all from the output of that jet. Well, it was putting out moisture, but for some reason, the one higher didn't form a contrail, the one lower formed a contrail, and that contrail kept getting bigger. How many have seen jets flying? You'll see a little contrail and it disappears. Now there's a lot of weird stuff going on about contrails. And people think contrails are, it's a government conspiracy to make contrails and all this kind of stuff. And I'm here to tell you that if that's some kind of conspiracy, they're throwing money away, because clouds are going to form because of the way that moisture acts in the air. So we're going to talk about how do clouds form, what does it take to make a cloud, and why they form the way they do. Now, I had to go this way because I have to establish root cause. I work in the nuclear industry. My business, I've worked in the nuclear industry for 46 years, over 46 years. And, one of the deals about working in the nuclear industry, we make power using an atomic process. And for some reason, the public is interested that we don't hurt anybody. So in my work at the nuclear industry, one of the things we do is quality assurance. And in quality assurance, we follow a standard called N45.2.11, which is an ANSI standard that says, here's how you must do your business to ensure quality. Now, does it mean that you'll never make a mistake? No. What it means is you're less likely to make a mistake if you follow this process. The process says, if you're doing engineering work, you are automatically in knowledge-based activity. That means that about 13% of the time you're going to make a mistake. Knowledge-based activity is something that you're creating you're initiating something. It's like you begin at the beginning and you're creating something new. You're not likely to get it exactly right the first time you try. So that's opposed to skill-based activity and procedure-based activity. Skill-based is something that you do every day and you don't make a lot of mistakes at it. Procedure-based, I got a procedure, I follow the procedure. And knowledge-based, I don't have a procedure and I don't have the skill. I'm figuring out how to do it right off the bat. So the way you ensure quality is you got an engineer who creates something, whatever it is, a design, a drawing, he's got some problem he needs to solve. So he starts with his assumptions, he starts with his skill and knowledge and the things that he knows about how the world works, and he develops a solution to the problem which he was given to solve. He then turns this problem, this work that he's done, over to somebody else. And the somebody else for checking. And the checker has to go through exactly the same process that he went through, but he does it independently. And he does it without reference to what this man did. So he does his own calculation, his own solution of the problem, and comes up with an answer. And if the answers agree, then you have confidence that the two people did it correctly. It's important when you do this that you maintain independence. And so the person who starts the process and the person who checks the process have to be separate. They got to work in their own environment. They got to do their own math. They've got to do their own analysis, and they come up with an answer. And if the answers agree, then you increase the confidence from a 13% error rate to a 2% error rate. Now that's one way you do it in the nuclear industry. We are required to follow this process anytime you develop stuff. The third layer is the approver. The approver is also independent. And he looks at the work of this guy, he looks at the work of this guy, and he looks overall and said, did you follow accepted processes? Did you follow the procedures you were supposed to follow? And did you do all of the things you were supposed to do in coming up with this? Were you in fact independent? And if he finds no holes and no barriers and then he will sign it. Approved. And that layer adds another layer. And there the error rate goes to about 1% or less. So it's a good thing that people follow this kind of process when you're dealing with an industry where the consequences can be severe. So in the process of looking at this cloud, I decided that I'm going to do root cause. And I'm going to approach the root cause independently. I'm not going to take somebody's word for it. Nullus in verba. Take no one's word for it. And by doing this independently and coming to understand how things work, how the world works, how clouds form, and how they are made, then I can come to a conclusion about this particular cloud, which would either confirm or deny the things that people are saying about the cloud. I'm not taking your word for it. You told me that, well, I think it's so-and-so. Well, fine. Did you do a root cause analysis? Did you do the math? Can you prove that what you guess is going to be there is actually what is there? If you haven't done that, you're just pontificating. You're just guessing. You're grabbing at straws. Root cause has to take a cause and a clear chain of events to the event. That clear chain has to obey the laws of physics. If it doesn't, you don't have root cause. You've got guesswork. This is like the two scientists up there and the scientist up here. He's drawing all these equations on the board. And the second one, he's watching, and he's sort of agreeing or disagreeing. The first scientist draws the equation, and he gets down to the bottom. And this is where he wants to be. He knows this is reality. But in the middle, he writes a statement, and a miracle occurs. And scientist number 2 is over here. He's, said, I think you have a problem right here. Well, that's where these people are. That's where people are. If you can't make a root cause chain of events, you're in that space and a miracle occurs. Which, actually, if you don't catch me by now, acts of God are miracles to us, but they're not miracles to Him. That's why I read Hebrews. Because by faith we understand that the worlds were created by the Word of God. The things which are seen are not made of things which do appear. Now, to do this, I'm going to take you down the road that I went down in order to discover this. And when I started off, I'll just be perfectly honest, I did not know where this was going to go. When you start off on a root cause analysis, you have to take the chain of events and the facts of the case exactly as you find them. Whether you like it or don't like it is immaterial. Facts are facts. You are entitled to your own opinion, but you are not entitled to your own facts. Because facts are facts. Now, Malachi, if you'd put up, let's see, have we got it ready to go? There it is. I'd like to go to slide 2. First thing I want to do is talk about units of measure. Now, this is going to be very boring and tedious to some of you. I can't imagine who would find this. You know, I don't think anybody willingly goes into this kind of stuff unless you just feel compelled to do it. But you were, when you went to school, you learned all these things, learned all these facts, and you said, I'm never going to use that. But here you are. Okay, here we are. We're going to, all right, units of measure. Now, the reason we use units of measure, first of all, laws of physics are just what is. This is the way things happen. And so in order to quantify it, to be able to make calculations, you have to put units of measure. You have to measure it somehow. And so there's some standard units that have been employed over the years that were developed over hundreds of years. And these standard units are how we measure things. That's so that we can write equations and make predictions. Equations and the mathematics that applies to science, the mathematics itself is symbolic of reality. It's not real. But the rules of mathematics are real. And so if you can say there's a relationship between these two things, then mathematics can be used to compute that relationship, and therefore you can do useful things. Like go to the grocery store and figure out what's the cheapest, the best value. Okay, that's mathematics. So math isn't real, but so we have these units that we use. Units of temperature. There's a whole bunch of, there's 4 different units of temperature commonly used. I'm going to use the international system of units for the most part here, which is something that those of us in America, particularly in Townville, South Carolina, probably aren't all that familiar with. But we're going to do that simply because that's the standard, and that's the way most of this data is recorded. And for the folks that are listening in overseas, you'll be perfectly familiar with it. Now, degrees Kelvin is not degrees Kelvin, it's kelvins. That's absolute temperature. And it's important you realize that temperature has an absolute basis. There's no such thing as negative kelvins. Absolute zero means zero. You cannot go below zero. It's the absolute. So kelvins starts from absolute zero and goes towards where we are. At freezing, the freezing point, which is 0 degrees Celsius, which is 32 degrees Fahrenheit, is 273.15 degrees, well, kelvins, not degrees, but kelvins. All right, when we talk about pressure, we're going to be using pressure in terms of millibar. Millibar is 1,000th of a bar, and 1 bar is 1 atmosphere. That's a standard measurement which has been standardized in order to make relative measurements. A bar is 1 atmosphere. The atmosphere is the pressure that the atmosphere exerts at sea level. Are we at sea level? No. How high are we? Anybody know? 750. Okay, I heard that. That sounds about right. We're above Lake Hartwell, but lower than Lake Kiowee. Lake Kiowee's at 800 feet. Hartwell's at about 650. And so we're about 750. That's about where we are. Is the air pressure at our location higher or lower than sea level? Lower. Okay, I'm glad you got that. So now, this means, does water boil at 212 degrees Fahrenheit here? No, because the air pressure's lower. Now, you might think, oh, that's just a fun fact when you're trying to cook eggs. But in fact, it has great relevance to atmospheric physics and where clouds form and how clouds form. So we're going to talk about that. All right, so pounds per square inch that's the pressure that we use, and we're all familiar with. We've got a good feel for pounds per square inch. Like we put 40 psi in our tires. We think about those, but so we got units. But we're going to talk about atmospheric physics in terms of millibar, and just remember, a millibar is 1,000th of a bar, which is 1,000th of an atmospheric pressure at sea level. Pretty close. All right. Next slide. Standard temperature and pressure. There's a standard temperature and pressure you use as a reference in order to calculate certain physical parameters. STP is defined at 20 degrees Celsius and 1,013.25 millibar, which is the same as 68 degrees Fahrenheit at 14.7 psi. So that's a standard temperature and pressure. When you measure things that can be compressed, like gases, then STP is an important reference point by which you make the relevant measurements. And the reason they chose that is because it's a pretty ordinary temperature and pressure. Ordinary temperature, not too hot, not too cold, pretty comfortable. Now, we also talk about mass, and we're going to talk about mass. The mass unit that we're going to use is grams or kilograms. Kilograms, 1,000 grams. But the gram is the amount of weight or the amount of mass of 1 cubic centimeter of water. Cubic centimeter, that's about a centimeter, about the width of my thumb. So you take a cubic centimeter, that's going to weigh at standard temperature and pressure about 1 gram. We're going to talk about length. The length will be in meters. And the reason we're going to use meters and kilometers is because that's the data that I've got. So, but a meter is just a little bit over 3 feet, right? You think it's about like that. That's about a meter, roughly. And then 1,000 of them. And then a mile is 5,280 feet, which is 1,601 meters. 1,601 meters, or 1.601 kilometers. All right, now, that's units. The next thing we're going to talk about is the periodic table. And the reason we have to talk about the periodic table is because there are elements that make up the atmosphere. Now, you can't see that. And in fact, I'm standing up here next to it, and I can hardly see it. So I've got a version that is a little bigger that I did. And these are the highlighted elements are the ones that we're going to consider in our study. There's hydrogen, atomic number 1, with an atomic weight of 1 gram per mole. Carbon, atomic number 6, atomic weight of 12. Nitrogen, 7, 14. Oxygen, atomic number 8, weight 16. Aluminum. The reason I want to talk about aluminum is because aluminum is the fuel that's used in the solid rocket booster. So that's an atomic number 13 with an atomic weight of 27. Chlorine, atomic number 17, which is a weight of 25. And argon, which is a constituent part of the atmosphere, is a noble gas, which means it's never combines with another substance. It's always an atomic. That's a atomic number 18 and a weight of 40. Now, the weight is just simply the protons plus the neutrons in the nucleus. Now, when you say atomic weight, what you're talking about is a mole of a substance. A mole is Avogadro's number, which is basically 60,000 billion particles. That's a big number. So atoms and molecules are really, really, really tiny, okay? They're so tiny that if you put 60,000 billion of them together, you'll get that many grams of a substance in its atomic weight. So 60,000 billion carbon atoms would weigh 12 grams. Grams, little things. Your little 1 gram of water it's not quite a mole. It's less than that because water weighs 18. So if you had 18 grams of water, you would have 60,000 billion molecules of water. That's a lot. Okay? Next slide. Let's go on. Now, I'm just trying to get this. The molar weight, remember, a mole is Avogadro's number of particles, and so a molar weight is the weight of the number of particles that is comprised by that many of them. 1 mole. And so the molar weight of hydrogen, which is always hydrogen in the air, is going to be H2. It's a molecule, not atomic. And the molecule of hydrogen will weigh 2 grams per mole. A mole of nitrogen combination molecule is N2. That's going to weigh 28 grams. A mole of oxygen will weigh 32 grams. And a mole of argon, which of course is a noble gas, is 40 grams. Now, all right. The reason I highlighted these is because nitrogen, oxygen, and hydrogen's a minor bit, that's not it, but nitrogen, oxygen, and argon are the 3 principal constituents of air. All right. So when we talk about the pressure that's emitted of a gas, the gas pressure is the combination of the pressures of all of the constituent parts of it. That's called Dalton's law. Dalton's law. The total pressure of a gas is a gas mixture is due to the partial pressure of each component gas. All right, so how much of the atmosphere is nitrogen? You can read the slide. 78%, right? 78% of the air is made up of nitrogen, molecular nitrogen. How much is oxygen? 21%. How much is argon? 0.9%. Those are the three constituent components. So 78% of the air pressure is due to the pressure of nitrogen. 21% of the air pressure is due to the pressure of oxygen. And 0.9% of the air pressure is due to the pressure of argon. What about the other 0.1%? That's everything else. Carbon dioxide, sulfur dioxide, all of those bad, nasty things. You know, people are worried about carbon dioxide. It's 0.04%. Okay? It's an important 0.04%, but still, that's all it is. It's in that 0.1% category. So the partial pressure of air. So now, what does air weigh? The weight of air, the molecular weight of air, is the partial pressure of air times the density of air times the component parts. And so the molecular weight of air is going to be mostly nitrogen, some oxygen, and a little bit of argon. And you wind up with a molecular weight of air of about 29 grams per mole. Now, this is important. It's important because air has buoyancy. And the buoyancy of air, the ability of air to carry something in weight, depends on the weight of the air. The law of buoyancy says that in order for something to float, it must displace its own weight in the fluid it's floating in. You got a boat? How many have a boat? I don't have a boat. Some people, I should now raise my hand. I don't own a boat. How many's ever been in a boat? Okay. The boat floats because it displaces the weight of water. So the water that's displaced by the boat being in the water weighs exactly as much as the boat. You get into the boat, what does the boat do? It sinks a little bit. How much did it sink? It sank by the amount that you weigh. Okay? Now, if you want to make something float in the air, what do you have to do? You have to have something that's lighter than the air, weighs less than air, that you displace so that now the air weighs more than what this does and it goes up. How many have ever seen a helium balloon? All right, 80 parties, helium balloon, you know what it is. Why does that work? What is the atomic weight of helium? 4 grams a mole, because it's got an atomic weight of 4. It's 2 protons, 2 neutrons. Well, is 4 grams per mole lighter than 29 grams per mole? By sure. And that's why helium balloons float. Okay? All right. Now, having established that, Dalton's law, partial pressures, we've now got to talk about the molecular weight of water. Water weighs 18 grams per mole. That's 16 grams for the oxygen and 1 gram each for the 2 hydrogens. So the molecule of water is 18 grams per mole. Is that lighter or heavier than air? It's lighter. So air that has a lot of moisture in it, humid air, weighs less than dry air. So what does the humid air want to do? It wants to rise. Now, so I know it feels, you go down to the coast and the temperature's 95 degrees and it's 95% humidity, and you walk out of your air-conditioned car and you think, I'm going to die. But the fact is, all of that humidity is in fact rising, and it is actually extracting heat from, it's cooling the surface is what it's doing. Because as it rises, it carries that heat up to the upper atmosphere. Now, what happens there is that, I'm going to need a drink of water here in a minute. What happens is, as the air rises, it cools off, and the moisture then will condense out and then emit that heat up into the upper atmosphere. So the water is a very, very important part of why our weather works the way it does. Extremely important. All right, now, humid air tends to rise. All right, now let's look at the water molecule. This is a very odd thing. A lot of people don't know this, but we're going to know it when we get done. Water molecule, the hydrogens don't connect themselves to the oxygen straight across. Because of the electron configuration of oxygen and the fact that it has a valence of -2, it wants electrons. And then the hydrogen then has a valence, can go either way, but it connects to the oxygen at an angle. And the angle is 104.5 degrees. Now, if you just look at this and you think, all right, since it's offset a little bit, thank you, brother. Thank you so much. Since it's offset a little bit, that means that there's an electrical potential that's associated with the water molecule. It's dipolar. Dipolar means it's got a positive side and a negative side. And it's because the electrons want to be pulled off on the side where the hydrogens are. Now, the fact that water has a dipolar, that has a little electric field associated with it, means that water wants to pull things apart by that electric field. So when you put stuff in water, it dissolves really, really well. Water is an almost universal solvent. This is the reason why. The dipolar molecule. But it also means that a water molecule is a little bit sticky. And that means that they want to attach to each other. They want to form structures and so forth where it has surface tension, a pretty strong surface tension when you're in the liquid state, and in the solid state it has a really high surface tension. Now, the reason that there's life on Earth is for the way the atmosphere is, but also because water is a part of it. 70% of the Earth's surface is covered by water. And even a good portion of the land is covered by water through lakes and rivers and streams and all of that stuff that goes on. All right. So water is an excellent is an excellent solvent. Now, water exists in 3 states. What are the 3 states? Solid, liquid, and gas. But the gas we're going to call vapor. Now, this might surprise you a little bit because you think of the vaporizer and you see the vapor coming off. The vapor you see is liquid. The vapor you don't see is gas, is a gaseous state. Is there water vapor in this room? Yes. How much water vapor is in this room? In the air? I don't know. Let me tell you, I did a little calculation. I can't, why would I do that, right? So calculation. I did a little calculation because I'm trying to nail this down. This calculation of the amount of water that is there is actually kind of important when you want to talk about clouds and how they form and how much material is there. This room is about 20 meters by about 20 meters by about 5 meters. So 20 times 20 times 5 would be about 2,000 cubic meters. 2,000 cubic meters, roughly, ballpark, okay? How much water would it take to bring the relative humidity of the air in this room from 0 to 100%? Turns out I've done the calculation, and the calculation is to take about 1 liter, 1 liter of water. Now, you mean I could completely evaporate 1 liter of water, and the atmosphere in this room would go to 100% relative humidity. Now, we're going to find out why that's true, because it's important in studying clouds. All right, Malachi, put up the next slide, slide 13. And I know that you can't see this, but you can see the colors. This is a state diagram, a phase diagram. And so the lower third of this is vapor, the blue is solid, and the green is liquid. Now, because water is the way it is, it has very well-defined parameters, a very well-defined transition between these states. This is so well-defined that it's actually becomes a way to do standard temperature measurements. So when you see the state diagram, this isn't guesswork. This is all developed from empirical data. That's a word you need to learn. Empirical, that means by observation. So experiments were done, and experiments were measured, and the parameters associated with the phase changes of water between these states was measured very precisely. And this has been going on for hundreds of years. In fact, Fahrenheit came up with his temperature scale based on the physical properties of water. Celsius also did the same thing. They liked Celsius better than Fahrenheit across the world, country. Fahrenheit, I guess, was British, and Celsius must have been French or something. Anyway, I'm not sure. But anyway, 0 to 100 degrees Celsius is the same as 32 to 212 Fahrenheit. And so, but the physical properties of water say that at certain temperatures and pressures, you'll find a transition between states. Now, it's important to realize that pressure is involved. If you bring the water molecules closer together by increasing the pressure, if we were to increase the pressure of the people in this room, we would squeeze everybody into fewer pews, right? You would get closer together. And so as you get closer together, you feel the influence of the other person more strongly. When your wife is standing across the room, you might not feel her influence quite so strongly as if she is right next to you. But in the case of water molecules, because of this dipolar attraction that it has, it wants to combine in various ways and attach itself to each other once you get the influence close enough where the electric field can become important. If they're separated by a far distance, then the electric field has small influence because electrically the water molecule is overall neutral. It's the same number of protons. It's not ionized, but it has a little local field. So you get farther apart, that local field doesn't make as much difference. And so now the water molecule's flying about in a gaseous state, and they've got lots of momentum. But if you pressurize them, then you get them closer together, and then that attraction can become important, and it can change into a solid state. Condense, or maybe go to a solid. So it could either to a liquid or to a solid. The temperature and pressure at which this happens is very well defined. As you go up in temperature, so the gas has much, much more activity. You've got to squeeze them together closer to get it to go to the liquid state. If you've got, if you're at a very low temperature, then you have to have very low pressure to keep it from going to the liquid state or the phase change. So to keep water as a gas when it's really cold, it has to be really, really far, really, really low pressure. So lots of distance. But if you're at high temperatures, then they got to be close together. So the density of the water follows this line, which is that curve that you see right here. Now you'll notice, well, you can't see it, but I can tell you, the scale on the horizontal, the x-axis, is temperature. And the scale on the y-axis, the vertical axis, is pressure. But I want you to notice that the pressure is not linear here. This is logarithmic. This is another one of those things you probably never knew you were going to need when you got out of school. The reason we use a logarithmic graph is because these changes in pressure are just too dramatic. They're too big that if you didn't plot on a log graph, you wouldn't be able to see the details of it. So, logarithmic scale, pressure, on the right side it's millibar, and on the left side is pascals, which is just another unit that's related to millibar. And across the bottom is degrees Celsius, and across the top is kelvins. But they're all the same relative units, so that it all fits on the same graph. Now you'll notice there's 2 points. Malachi, blow that up just a little bit, if you would. All right, right there is a point right in the middle, And then another circle over here to the right. One says solid, liquid, vapor, triple point, and the other one's boiling point at STP. Or excuse me, no, it isn't. It's at atmosphere. The freezing point's at STP over here at the top. Now, water has a unique property in that at a very specific temperature and pressure, it can exist in all three states at the same time. Now, a lot of substances have triple points, but water is really particularly important to us because of how it relates to clouds and the way we live. The triple point of water is so well defined that it's used as a measurement reference. So if you want to calibrate your thermometer, you can go do a triple point experiment, stick the thermometer in there, and if it doesn't read 0.01 Celsius, the thermometer is broken, because that's the temperature. The pressure is 611.657 pascals, which is 6.11657 millibar. Same, just you one scales to the other, and that's how you get it. So 6 millibar. Now, what's the pressure of atmosphere at sea level? You remember what I said? I've lost the class. It's about 1,000 millibar, right? Okay, so this is 6 millibar. That means that's 0.6% of the pressure at standard atmosphere. So it's a really low pressure. But it's really low pressure, and at this temperature of 0.01 degrees Celsius, or 273.16 Kelvin, water can exist in all three states, gas, liquid, and vapor at the same time. Okay? Why is this important? The reason it's important is because when we're talking about clouds, in the upper atmosphere, the pressures are low and the temperatures are low. So we're actually on the bottom end of this curve over here, this side of the curve, where it goes between vapor and solid as opposed to vapor to liquid. Now we see water go from vapor to liquid where we live, and we like it that way. But in the upper atmosphere, it actually gets colder. All right, so the change of state, if you can imagine what the, oh man, I can tell I'm fixing to lose everybody. When you go from one state to another state, when you go from liquid to vapor, it doesn't all happen at once, right? How many has heard a term called heat of vaporization? Some of you have. All right, a few of you have. The guys have heat of vaporization. What this means is there is a difference between heat and temperature. This is, sorry guys, but this is your physics lesson. Wake up. All right? You're going to run into this in school. And now, since you don't, when you go in school, the teachers don't understand it, so they can't make you understand it. But we understand it. So here's your chance to grab onto it. There's a difference between heat and temperature. Now, if you are in the liquid state and you add heat, the temperature changes, right? Add heat. Heat is energy. Temperature is a measure of molecular momentum. Two different things. They're related, but they're not the same. So temperature can change if you change heat as long as you're in the same state. If you've got all gas, you add heat to the gas, it'll heat up. Temperature will rise. But what about the transition between liquid and gas? You add heat and the temperature doesn't change. What happens is the amount of water changes from liquid to vapor. So this point at which water transitions between liquid and vapor is called the saturation point, saturation line. Now, I can talk about this with some degree of confidence because I work at a power plant. and we boil water for a living. Okay, that's what we do. We boil water. We take water, liquid, we add tremendous amount of heat to it and turn it into a gas called steam. The steam goes through a turbine where that energy is extracted by transfer of momentum. So you remember I said the molecular momentum, temperature is a measure of the molecular momentum. Well, if you take the momentum away from the substance, then it lowers temperature and pressure. So the turbine takes the momentum of the steam, turns it into torque in the turbine, lowers its temperature and pressure through the stages of the turbine. When you finally get to the bottom end of this whole process, you wind up with steam that has very low pressure, relatively low temperature, and lots of volume. Huge volume. So you started off with water with like a volume like this, and when you get to the end of the turbine, the volume is like this. So how do you get it back to water? You condense it. So you run it through a condenser. The condenser is at a lower temperature than the steam saturation, and it condenses that volume back to liquid again. Big volume, back to liquid, little volume. And then you pump the water back through to heat it back up again and make the process. So the whole thing just keeps going. Now, water transition across these phases takes lots of heat, but doesn't necessarily change the temperature. So this is how the atmosphere cools the earth. You take water. Water is one of the most important cooling mechanisms for the earth. The surface of the earth heats up. The water is driven into the vapor state at an ever-increasing rate because of the additional temperature. That water then, being lighter than air, mixes with the air, and it carries up into the upper atmosphere. As it goes up into the upper atmosphere, it carries all that heat with it. It gets to the upper atmosphere, the heat is released through condensation, and the condensation is clouds. And as it releases that, as it condenses, means it's transferring that heat to the upper atmosphere. So the heat came from down here, wound up there, got transferred up there, and now it can radiate into space, which cools the earth. So the earth gets its energy from the sun by radiation. The radiation heats up the earth. The earth gets rid of its heat also by radiation. So the earth radiates heat into outer space. The earth receives energy from outer space. The balance of those two is what is how we wind up with our weather and our temperatures, and why it's cold in the winter and hot in the summer, and not too hot and not too cold. Just right for life to exist on this earth. All right, now this saturation line, pull it back out again, Malachi, so we can see the bigger picture. Actually, it continues on. You see it stops at the bottom of the graph, but that continues on in same orders of magnitude and temperature. It goes way down. What that means is that the vapor pressure of air, the vapor pressure of water, the partial pressure of the water is what's important when you're talking about where clouds form. It's not the air pressure that matters, it's the pressure of the water that matters. So the water pressure, by Dalton's law, if you start from a vapor in the gaseous state, then the pressure of water is part of the pressure of the air, all the other things that are there, because it's in a gaseous state and the gases mix. So the partial pressure of water is what's important when you go to make a cloud. Now, I'm just about to the point where we can start talking about genuine atmospheric physics. And I know that this has been a Earth, you've really been on the edge of your seats. But I have to go through this because none of this is magic. None of this is magic. And that cloud that appeared in 1963, February 28th, was not magic. It's physically there. It wasn't somebody's imagination. And so if it got there, there's characteristics associated with that cloud. And they have to obey the laws of physics. You're not, you know, it's very easy for us to trivialize things. It's oh, well, it's just, you know, blah. And I don't want to minimize this, because there's a big difference between faith and science. And in fact, you cannot prove science by faith. You cannot prove faith by science. You cannot prove God by science. We're not setting out here to prove God. What we're showing is that if that cloud exists, it has to obey the laws of physics. It must. And if it obeys the laws of physics, then we'll be able to pin down and say, here's a reason that just won't work. And if you say that this cause is the reason for that cloud, you've got to have the chain of events that obeys the laws of physics. And if you can't get there, you don't have root cause. Now, when I started on this study, when I started on this, I went back to first principles. Because if you can't go back to first principles, then you have to take somebody's word for it. And that's where most people are. Most people are just going to take, well, he's an expert. I'll take his word for it. You don't do quality assurance that way. If you're going to prove something, you've got to be able to prove it yourself. Otherwise, you're just taking someone's word for it. Now, there are some things that I will take a man's word for. I'll take a prophet's word. If the prophet says something, he's got insight into things that you and I don't see. He's got prophetic. He lives in two worlds. He lives in a spiritual world and he lives in a physical world. And he's seeing things that you and I don't see. And if he tells you what he sees, if he's honest, an honest man, an honest prophet, he's going to tell you what he sees. But he can't tell you that what he sees is necessarily perfectly, how shall I say, you can't necessarily conjure it up from the laws of physics. Because you're dealing with God. The last time I testified, I'm going to just bring this up again, just so you'll realize how important this is. The laws of physics always work in this reality. We live in this reality of this four-dimensional space-time that we're in. They always work. Thermodynamics always works. If you do an experiment, it will obey the laws of physics. If you didn't find in your experiment that it obeyed the laws of physics, your experiment's broken. You did something wrong. It's that positive and that sure. But when God intervenes, He exists in another dimension. So, when Jesus fed thousands of people with a little boy's lunch, it was perfectly, let me tell you, all of those people got fed. The laws of physics worked for all of them. It was substance. There was energy in that food. There was proteins. There was everything the people needed to survive was in that food. All the laws of physics obeyed. But it didn't get there by physical means. By faith we understand the things which are seen are not made of things which do appear. That's why I read that verse in Hebrews. All right, we are almost halfway through our journey, and it is time to go. So how many are ready to come back this evening and hear the rest of the story? So I said that because people are trying to disprove the manifestation or something that God did in our hour, and they're trying to disprove it in a way using intellectual reasoning and by making a correlation between an event and another event. And it's true that the correlation is there. But it's a very important principle in science that correlation is necessary, but it is not sufficient. For something to be true, it has to indeed correlate. They've got to, one thing follows another. Response cannot precede excitation, as they say. So that something happens and then there's a response to that. But just because you see a correlation of things, this happens and then this happens, doesn't mean they're related. And in fact, if something is truly related, there will be an unbroken chain of circumstance that will go from this event through positive coupling of laws of physics to the other thing, which you would then see manifested. Now, we depend on this to be true. In your work, in your whatever it is you accomplish, what you do in your daily life, you depend on that to be true. I mean, could you imagine what would life be like if the I don't know, I can't do what if cooking your food just didn't work? You went to cook your food and you put it on the burner and you pull it off and it's frozen. Well, or you stick it in the refrigerator and it comes out all steamy and juicy. I mean, you would say something is wrong here. This picture is not correct. The laws of physics have been suspended somehow. And you would all find this to be laughable because you are laughing. Some of you are. But that's what you would have if you don't have a direct chain of cause and effect. Real cause and effect. And so when we approach these things, we approach them not to prove that God is God, because you can't do that anyway. You accept God by faith. And if you can't accept God by faith, then you're like I was when I was a young man. When I grew up in the Baptist church, and they taught me all kinds of things that they thought were God. And they taught me that the Bible contained the Word of God. But they never taught me that the Bible was the Word of God. And when I finally made that connection, and I realized that the Bible isn't just a nice book, that it actually contains the Word of God. And when that was made real to me, I lifted my hand in a meeting one day and said, Lord, I accept a God who wrote the Bible. And I called upon that God, not the God of the Koran, or the God of some mysticism, or the God of some book, or the God of some philosophy, or the God of some church, but the God who wrote the Bible. And He changed my life in a heartbeat, literally. I raised my hand, and 100-pound weight lifted off of my shoulders, and I was instantly changed. Now, from that experience, I know that I met a person who has the capacity to do things that psychology can't do. And if you think, oh, Brother Bill, he's just enthused. No, I'm not. I was changed. I am enthused, but I'm not just enthused. It is true that I'm enthused. All right. When we took up the subject this morning, we were talking about the properties of water. And the reason we're talking about the properties of water is because we are concerned with what it is that makes clouds and how clouds form. This is a cloud. There's a photograph of the cloud. I've got the magazine that it appeared in right here. There's a live copy of the magazine. And I think I actually have a couple of these, but this is the only one I could lay my hands on right quick. And on page 112 is a picture of the cloud and some comments that were made by the reporter who reported from a Dr. James McDonald, who's a professor of atmospheric physics. I found where all of Dr. McDonald's writings are archived. It's at Princeton University Press. And I found his website, and he actually talked about this cloud on several occasions, not just once. His first publication on the subject was in April 19th, 1963, in the magazine Science. Now, I don't know about you, but I'm not a regular reader of the magazine Science. I don't suppose that this would count for popular literature. But the magazine, Science magazine, which was a publication of the American Association for the Advancement of Science or something like that. Anyway, it's all the same. Science magazine. It was a reputable, very prestigious magazine at the time. And in that, he actually made some comments about the cloud, which they repeated some of them in this Life magazine article. For example, how high it was and how big across it was. 30 miles high, 26 miles high and 30 miles across. Dr. McDonald had figured that out from studying photos that were taken. As soon as the cloud appeared, he was alerted to the existence of a cloud by a friend. Friend calls him up, knows he's a professor of atmospheric physics, said, this is something you got to see. He walks out his door, and he's in Tucson. And he looks up in the sky, and there's the cloud. Looks to the north. So he's in Tucson and can clearly see the cloud. And he says, I've never seen anything like that before in my life. And it's true. Nobody had. So he gets on the phone, he calls the newspaper, he says, I want an ad put out, I want this on the radio, I want everybody who takes a photograph of that cloud to send them to me. He gives the address, I'm studying this, I want to find out what's going on. So from the photographic analysis and his analysis and the things he knows about atmospheric physics, he is wowed, because this is something that's really unprecedented. And you use that word, you hear it all the time, and it doesn't mean what it meant then. So he gets 150 reports by the time that he writes this article in April 15th, April 19th is when he writes the article. Now, in this, he gives estimates of the size and the geometry of this cloud. And I'm going to use his estimates when we get a little bit farther in here. The reason I'm going to use his estimates is because, one, he did the measurements. And number two, his estimates are conservative. The estimates that he gave of the size of the cloud on April 19th was smaller than the estimates he gave in an article in a later publication in June of 1963. So he says that the cloud is a certain size, and when he gives that size and that dimension, it was a little bit smaller than what I had calculated based on my analysis of the cloud. So I did some independent analysis and said, well, it's about this number, we'll just use it. And then I find where he says how big it is, his is smaller, I'm going to use his numbers. Not because I think I was wrong, but I am uncertain. And in uncertainty, you take if you're trying to find root cause, you have to err on the side of uncertainty that will make it clear that you have excluded some possibilities. So if I take a conservative estimate of the size of the cloud, I can then draw a line with great certainty that it is not smaller than this size that I say it is. In fact, I have every confidence that it's actually bigger, much bigger. But if I take the small number, I can show by analysis that certain potential causes are excluded because they don't meet the criteria of even that minimum amount. Now, this is important. We're going to use this to show just how big this cloud is. Now, I want to continue in our discussion, and the next thing we're going to talk about, since we've talked about the properties of water, and the saturation line and the sublimation line, and that curve, everybody remember that? I don't need to put that back up there, do I? Okay. I'll be glad to put it up there. We can spend the next 3 or 4 days talking about it, okay? All right, so I want to put up, Brother Malachi, if you would, go to slide 18, if you would. 18. Hey, listen, we're almost halfway there, by the way. There's 41 slides. So 18 is almost halfway. But these will go a little quicker because we don't have to spend quite so much time on them. Atmospheric layers. Okay, there's 3 principal layers of the atmosphere. There's actually more. There's one more above that. But I'm not going to worry about it because it's way outside of where we want to worry about. We live in the troposphere. What happened? There it goes. Okay. We live in the troposphere, what they call the troposphere. That's the atmosphere from sea level up to about 12 miles, 18 kilometers. I'm going to give it to you in kilometers because of the way the next slide comes up. So the next layer is called the stratosphere. And that's from about 18 kilometers up to about 50 kilometers, which is 12 to 30 miles. And then the layer above that is called the mesosphere, which is from about 50 kilometers to 100 kilometers, or about 30 to 60 miles, in that range. Now, the cloud, if you recall, was how high? 26 miles. So what layer of atmosphere was the cloud in? The stratosphere. This is really important. All right, now how do they determine what layer is what? Well, the way they tell what layer is what, the troposphere, the stratosphere, the mesosphere, has to do with the temperature profile that's associated with the atmosphere. So now let's go to slide 20. All right. Now this slide, I don't know how clear this is to everybody. Again, the numbers are probably too small. You can't see it. But the horizontal axis on the pressure, which is this side, is logarithmic. Everybody see that it's logarithmic. Okay, it means each major division is a factor of 10. So you start with atmospheric pressure at 1,000 millibar. You go to 100 to 10 to 1, 0.1, 0.01. And you can see that the pressure in millibar is 0.01 millibar at an altitude of 80 kilometers up there at the top of the mesosphere. Now, you'll notice that that's kind of a straight line. It looks pretty straight. Okay, so what that says is, and I apologize for the math, but you'll live through it. The rate of change of the pressure is proportional to the pressure. When the rate of change of something is proportional to its value, the solution to that is always an exponential function. It's a logarithmic function. All right, I got some mathematicians that are doing this. I'm okay. All right, so, and this shows graphically, you can see that. If we've got a straight line, which it looks pretty straight, and the horizontal axis, the x-axis, is logarithmic, then you know that's a logarithmic function. And that's the way the pressure changes in the atmosphere. So as we start off, atmospheric height linear, but the pressure goes down logarithmically, factor of 10 at a time. If you go up to the value that's about 40, right at just above 40 kilometers, and you look at that pressure, you'll see that it's about 2.2 millibar, or 2 millibar. It's right close to that. That's important because of where that is on a saturation line. And the temperature, now let's look at the temperature profile. The temperature profile starts off, again, we're going to use kelvins because 0 Kelvin is absolute zero, and we're well above absolute zero, at least some of us are. And so the standard atmosphere is well above 280 kelvins. What that means is it's fairly warm at sea level in the standard atmosphere. But as you go up in the elevation and the pressure goes down, what is the temperature doing? The temperature is going this way. In the troposphere, the temperature is going down as you go up in elevation. Now, all of you people who have flown in commercial airlines have seen this. You fly in the commercial airline and they'll put up the little sign and they'll tell you what the temperature is outside. Anybody tell me what's the temperature at 38,000 feet? 60 below. Brothers paying attention. 60 below, so it's minus 60 Fahrenheit. Or if it's Celsius, it's still not too far, minus 55, minus 50 degrees Celsius. So it gets colder as you go up. So as we go up in the atmosphere, it gets colder. Now, but at the top of the troposphere and the beginning of the stratosphere, the temperature does a strange thing. It stops going down, it turns, and it starts going up. So as you go up in altitude, up to the top of the stratosphere, the temperature is increasing. Now, I can tell you why, but let's just observe that that's the way it works. Well, I might as well tell you why. This is also the ozone layer. The stratosphere is where the ozone is. And the ozone absorbs energy from the sun. Everybody knows that ozone absorbs ultraviolet energy. That's actually an important thing for us. We want the ozone to absorb the UV so that when we go out on the beach, we don't get killed. This is why you put, you put sunscreen on, right? Or you wear long sleeve shirts. But you cover yourself to protect yourself against ultraviolet. Ultraviolet radiation is much stronger as you go higher in the atmosphere because it comes from the sun. And so the UV, the ultraviolet, which is very penetrating and can ionize, has the energy to ionize molecules, create free radicals, the ozone layer absorbs that UV and helps protect the Earth. So it's important, but it's absorbing energy, and as it absorbs energy, it gets warmer. And so the stratosphere is heated by the energy that it absorbs from the sun. Now, why does it go down in temperature as you get up to the bottom? Why does it go down as you go from the troposphere? Well, the reason it goes down is primarily because of the properties of water. And also the properties of the fact that the Earth radiates energy, loses energy into space from that altitude in that layer. So the temperature goes down because that layer of atmosphere is radiating energy into space. Losing energy, temperature goes down. The rate at which it goes down has everything to do with the properties of water. Now, because water is carrying a tremendous amount of energy as it evaporates And as you go up in altitude, the water that's in the atmosphere is going to reach a temperature and a pressure where that pressure, it'll begin to condense. And when the water condenses, we have clouds. So how many looked at the clouds coming in this evening? One or two. Nobody's paying attention to the clouds. I looked at the clouds. I said, wow, look at those cirrus clouds up there. All right. So here's the key. The temperature goes down until you reach a certain altitude. Then the temperature turns and starts going up. It is those temperature transitions that determines which layer of atmosphere you're in. Now, just for... I want you to just put up Malachi. Go to slide 35 just for a moment. We're going to get this. All right. Now, I did this calculation in my math program that I have. And this is a calculation of the saturation temperature of water as a function of the pressure, the atmospheric pressure, compared to the normal atmosphere pressure. So here's the normal atmospheric temperature, and then what you have is the saturation temperature for water. You see the correlation. Here, as the normal temperature is going down, as it does as you increase in altitude, the saturation temperature, that is the temperature at which water goes from vapor to liquid or vapor to solid, along that line. You remember the chart that was up there this morning. They correlate perfectly up till you get close to the top of the troposphere. Now, what this means is you are condensing the water out of the air as you go up. And so the air is actually drying out. It is removing water from the air. It's condensing. The water that's condensed eventually winds up where? In a cloud, which when it gets dense enough, guess what it does? It rains. And so the cloud actually rains out. And so the water that was evaporated gets into the upper atmosphere, gets condensed as a dense substance, and then it gets too heavy to be supported by the atmosphere, and it falls, and it rains the earth. So that's how you get the water from the ocean over the land to bring the rain. Now, you'll notice what happens when you get up to the top of the troposphere. The water quits following that curve. And the reason is you've wrung all the moisture out of the air. And if you wring all the moisture out of the air, there's no more moisture up there to condense. You've already condensed it out. So when you see the temperature going up and the saturation temperature of the water going down, that means that you cannot make a cloud. It's impossible to make a cloud in the stratosphere because the water is now at a vapor pressure that's so low you can't make it condense. So you're way over on that side of the phase diagram. It is true that the pressure is going down. As you go up in the atmosphere, the pressure continues to drop. But the water density goes down even faster. And so when you get to the stratosphere, clouds won't form. Nobody has ever seen a naturally occurring cloud in the stratosphere. It just doesn't happen. And the reason it doesn't is because the moisture content of the air gets wrung out as you go up in altitude because it gets cold. And when it gets cold, the water condenses out. Now, there's a publication that I actually downloaded the standard atmospheric tables to make this calculation off of. And it's the Air Force Geophysical Laboratory, Air Force Geophysics Laboratory, atmospheric constituent profiles from sea level up to 120 kilometers in altitude. Actually goes up into the thermosphere, above the mesosphere. And from this, what you'll find out is that water starts off at some constitution based on its temperature, and the more heat you have, the warmer the air is, the more water you can carry in the atmosphere. This is I hope I say this right, is the Clausius-Clapeyron equation. Predicts what that correlation is. We're not going to go into it. We're going to cover it. I won't charge any extra for that one. All right. So, but everybody knows when it gets hotter, and if you're in Phoenix and it gets hotter, or if you're out west and it gets hotter, it just gets hotter. But it's a dry heat. But if you're in Charleston, South Carolina, and it gets hotter, you're in trouble. Or Columbia, South Carolina, or Athens, Georgia, or Valdosta, Georgia. And it gets hot, and it gets muggy, and it gets miserable. As I've often told people, I said, if it wasn't for air conditioning, nobody would want to live in the South. But all of that heat, all of that moisture, as you go up in altitude, it gets cooler and it gets drier. Now, the amount of moisture that you can carry is, up to a few percent. We'll just say that. A few percent of the total atmosphere on a hot day, hot muggy day, down here low, you can get quite a bit of water in the atmosphere. But at the altitude of 12 miles, the amount of water that's in the atmosphere is around 5 parts per million by volume. So you're down to 5 orders of magnitude, really 6 orders of magnitude less water than you'd have down low. Orders of magnitude, what does that mean? Factor of 10. That's what it means. When I say orders of magnitude, I say that to give you an idea of just how big the range is. 5 orders of magnitude is a factor of 100,000. So the moisture gets wrung out of the atmosphere as you go up in altitude. Now, once you've wrung the moisture out of the atmosphere, it doesn't just suddenly magically appear again. The only way gases have of mixing is by diffusion. Diffusion means they're bouncing around, they're a gas in a gaseous state. They bounce around amongst themselves and they mix. So they mix so thoroughly that if I took a small sample of the atmosphere, it would be representative of the whole. So they thoroughly mix, so the water thoroughly mixes, except water is different than all the other constituents in the atmosphere. Water is different because it has this ability to condense and change state in these temperature ranges where we live and where it's important. So the water dries out, and you're going to hear, if you read Brother Branham enough, and he talks about this cloud, he says the same thing. But he tells you that in his own language and not in the language of this physics. But he's perfectly correct. He's exactly right. He says there's no moisture up there. Well, I want to get really technical. Then there is moisture up there. It's just 5 parts per million. Which, for all practical purposes, there's no moisture up there. There's a way to say that is there's no moisture up there to make a cloud. And there isn't. Put the next one up. All right, here's the same curve, but in terms of pressure. So here's the saturation. Remember, it's temperature and pressure that correlate on that line where you can transfer states from one to the other. So here's the pressure curve. Now notice I had to put the pressure and plot it logarithmically. If I didn't use a logarithmic scale and used a linear scale, you'd have this line that goes zoom down to zero, and then it's just this little teeny thing over here, and you could never make out any kind of accuracy or sense out of it at all. So we put the pressure in terms of logarithmic scale. And if you look at it, at the altitude of the cloud, 41, 42 kilometers, I tried to get it in the right spot, but it's a little bit, just a tiny bit lower than where that line is, but not much. You'll see, you can count them, 1, 2, 3, 4, 5 orders of magnitude. There's 100,000 times less water than is necessary to make a cloud. And what that tells you is, if there's a cloud in that space, it was put there deliberately. It never happened accidentally. And it never happened from any natural process. Now, you could not say that in the troposphere, in the lower part, because clouds happen in this part of the world all the time. This morning I mentioned, Brother Josh, you remember our discussion about the jets. And we also know that the altitude of a cloud depends on the specific humidity conditions and the specific temperature conditions. And these conditions actually can change a little bit. You can have what's called a stable atmosphere, where the temperature goes down slower than the vapor pressure of the water goes down. And when that happens, the air is considered to be stable. If, however, the temperature goes down faster than the water vapor saturation temperature goes down, then we have what's called an unstable atmosphere. Because the water vapor, as it gets cooler, condenses and actually reduces the pressure even more. That creates a low pressure region which continues to suck energy out from the bottom and throw it up into the atmosphere. This can be very aggressive. And you can have storms in this unstable atmospheric condition that will just keep feeding on itself and feeding on itself and feeding it, keep pumping moisture. And you can develop circulating currents that will actually, with enough velocity in the current, to support heavy stuff, like as the rain develops and builds big droplets, it can still be maintained by the fact of these updrafts can just keep it up there. And they can freeze and turn into hail. And the ice particles can be supported by this rapid updrafts that can occur. But finally, you always reach a point where the energy is satisfied, and then all of that stuff that was supported by all of these updrafts comes down. And when it comes down, it's thunderstorms, heavy rains, hail, whatever it was it created up there by those unstable atmospheric conditions. Now, that's not the condition that we enjoyed today. Today, we're more or less under what's called a stable atmosphere high pressure condition. The high pressure condition, the dry air from up top is pushed downwards, raises our pressure, but it also means that we have insufficient moisture to support these updrafts that would occur from the water condensing along that saturation line. So stable atmosphere, high pressure. Unstable atmosphere, low pressure. So when your barometer goes down, what do? When your barometer starts going down, you say, oh, we're fixing to go into a low pressure region. That means we're going into an unstable atmosphere. That means bad weather's on the way. How many has taken lessons in meteorology for some? Okay, how many of you have a pilot's license? Okay, one. since I didn't see any hands, but I have a pilot's license. And meteorology is one of the things that you study to get your pilot's license. And you study clouds because they're really important if you're going to fly around. All right. Now, you notice then the saturation pressure margin for the cloud is way, way, way off from where a cloud would naturally form. This is why that cloud was so unusual. Now, let's go to Malachi. I want to talk about winds aloft. Winds aloft. That means the winds going through the atmosphere as you go up in the atmosphere. So if you would go to that website that we were talking about earlier, winds aloft. Winds aloft. All right. Yeah, drag it up just a little bit. Okay. Now, go to the earth and go to, all right, this is the surface winds. The little dot that he put up there is where Flagstaff, Arizona is. So it's about 100, and go back down. There you go. So it's about 35 degrees north. The latitude is about the same as our latitude here where we are. So if you can imagine, if you headed due west from our present location, you would wind up due west, this way, you would wind up over Flagstaff, Arizona, pretty close. And the longitude, that is around the Earth, starting from the prime meridian in Greenwich, England, and you come around so many degrees, at 111.5 degrees is Flagstaff, Arizona. That's about where the cloud was, pretty close. So we're looking at the surface winds. Now, I have not looked at this today. This is, you and I are looking at this for the first time today. But I've been watching this website for quite a while. This is earth.nullschool.net. And it's very interesting. Give you all kinds of information, and they'll give it to you all over the world. Scroll back out and show you that. Yeah, keep scrolling. So there we are, a little spot on the world, and that's where we're located. So as we come back in, surface winds, you can see what it is. Now, the reason that they can do this, first of all, I got to tell you that this is not actual winds. This is a model. But the model is benchmarked against actual winds every day. Twice a day, they benchmark it. And so they know from the laws of physics what the differential pressures are going to do, and so they can predict what the winds are going to be, and they continually update it so that it's accurate. Now, at the surface, that would be the winds. Let's go to the next layer up. Oh, where's the mouse? There he went. Okay. So let's go to 1,000 millibar. Now, in Phoenix, that's still surface because it's up about 3,000 feet. So let's go up to the next layer. This is really hard. There it goes. 850 millibar is about 5,000 feet. So that's just a couple of thousand feet above Flagstaff. And there you can see the wind is at 10 degrees at 52 kilometers an hour. Let's go to the next one. 700 millibars is about 9,000 feet. So we're getting up pretty high. This would be like the top of the mountains. And you can see the winds there has shifted a little bit, 20 degrees at 38 kilometers an hour. Let's go to 500 millibars, about 18,000 feet. And notice the direction has changed, but the speed is still about 29 kilometers an hour. At 250 millibar, now the direction is coming almost from the west. Why don't you pull it down a little bit? All right, now we're going to look. This is the jet stream. 250 millibar is about 34,000 feet. This is where the jet airplanes fly. And the reason they want to get up into that jet stream, because if you're flying from west to east, that saves a lot of gas. You get this nice tailwind and you just scream. But notice that, got all these streams, and the colors actually indicate the velocities, but the particular velocity is a little bit faster in some places and it's a little slower in other places. All right, let's go to the next elevation. At 70 millibar is about 60,000 feet. This is the top of the troposphere, bottom of the stratosphere. Now notice 270 degrees, so that's almost due west. And you'd think, ooh, that looks, But look at the velocity. It's 50 kilometers an hour. It's actually slowed down a little bit. All right, so let's go up to 10. This is 100,000 feet, 265, almost due west. But it's at 65 kilometers an hour. 65 kilometers an hour would be about 40 miles an hour. Now, if you had 3.5 hours to get a rocket debris from one location to another location, 3.5 hours, 510 miles, could you get there if the speed was only 40 miles an hour? No. It has to be 135 miles an hour. So we can see that in order to get, remember what's important, it's not the winds down here at the jet stream where it's really fast. What's important is the winds up at this altitude where the cloud is. And that's nowhere close to those kinds of velocities. Now, I've watched this website over the years, and I can tell you that in the summertime, that's the wrong direction. It blows from the east. And it's hard. I mean, it's easterlies. Down in the lower atmosphere, it's westerlies, just like you expect. But as you go up, the wind direction changes, and it actually blows at that high altitude. It actually blows from the east. But it doesn't matter. Now, here's the point that I want to make. You can see that the winds are not local. They're not little local winds. This is a wind that is spread out over a large area. And so the wind that I would measure in Flagstaff, Arizona is characteristic or indicative of a much larger area. And we know what the wind direction was on February 28th, 1963. They didn't have this tool, but they did have people on the ground observing which direction the cloud was headed. And they also know what direction, they also know how fast it was going. So, put up slide 72. If you would, Malachi. We're going to close it now. Slide 72. I said 72. I meant 22. I'm sorry. I can't read my own writing. All right. The thrust-augmented Thor missile, a Gina D missile, was destroyed by the range safety officer at an altitude of 44 kilometers, which is high enough. But they launched the rocket and destroyed it at 1449 Mountain Standard Time. It was 1349 Pacific Standard Time, which is local time. But I converted everything to Mountain Standard because it's one time zone to the east. And so it was seen at 1822. That's when the cloud first appeared. Now the picture that we have was taken a little bit later, maybe 20 minutes. But the cloud first appeared and first became aware at 1822. So the cloud was there 3.5 hours after the rocket was launched. What direction was the winds? the distance would have to be 522 miles from where the missile was destroyed over Flagstaff, plus or minus 510, 520. Professor McDonald said 510. It doesn't matter at this point. To be viable, the winds have to blow at 149 miles an hour if it's that much distance over that amount of time. 149 miles an hour is 240 kilometers per hour. Did we see that kind of speed? You didn't see those kinds of velocities at that altitude. That's the 10 millibar level, which is actually lower than where we're talking about, is 100,000 feet. That is well into the stratosphere. All right. But we also know what direction the winds were blowing. The winds would have to blow from a direction in order to get to that spot at 265 degrees. Now that's actually about the direction of the winds that we see right now. But the winds were actually measured to be blowing out of the northwest. So when the cloud, you saw the cloud and they looked and saw, oh, it's moving. They could tell that it's moving. In spite of its huge size, they could see that it was moving. And so they calculated, eyewitnesses said, oh, it's moving towards the southeast. So the direction of the cloud is about 310 degrees, not 265. So the actual direction of the cloud is the wrong direction. If the wind is blowing at 310 degrees at Vandenberg Air Force Base, like it is in Flagstaff, the debris from the missile is going to wind up in Mexico, in Baja California. So we can say just from the direction of the winds that were observed on that day, plus the characteristic velocity of winds at that altitude, the rocket couldn't have done it. It's not viable. Now we're going to talk about that rocket, and we're going to look even more in detail as to what was going on. So, Dr. McDonald estimated the speed of the cloud from photos. From the pictures that were taken and the times that the pictures were taken, he was able to ascertain through triangulation the direction and velocity of the cloud. It was less than 95 miles an hour in a direction of about 310 degrees. Now, you cannot get a rocket from Vandenberg Air Force Base to Flagstaff with the wind blowing that direction at that speed. It just simply won't work. Now, there's more. Let's talk about the size of this cloud. Let's go to the next slide, 23. In Professor McDonald's first publication, he estimated the size of the cloud. And I said, okay, I'll use his estimate. He first estimated that the cloud was the length of the ring that was made was about 60 kilometers, and the width of the cloud was 3 to 4 kilometers. Now we're going to do the math, but we're going to do the math using minimum numbers. He later, in a later publication, said that the cloud was actually bigger than that. So at first he thought it was about 30 miles wide and so forth. But then later he said, no, it was 30 miles wide and 50 miles long. Now, most people have no concept of how big this cloud was. And one of the reasons that you don't have a concept of it is because, as we said this morning, clouds are fractal in nature. You look at a cloud, you can't tell just from your vision how high it is. Unless you're really experienced and you'd say, oh, that's a cirrus cloud. It's got to be certain altitude, or a cumulonimbus or a cumulus cloud. You'll see these different elevations. But unless you've got an instrument that measured it and says, here's the altitude of the clouds. Like, what's the ceiling? You know, and then they'll give you a description. If you call the airport and dial up AWAS, they'll tell you what the conditions are. They'll say, well, how high the clouds are and this and so forth. So they'll tell you, but you can't really tell without that instrumentation, because they all look self-similar. But if you're standing in Flagstaff, I just imagine you're standing right underneath this cloud. You look up in the sky and you say, that's a big cloud. 30 miles is a 60-degree angle. That means 1/3 of the sky is occupied by that cloud. So if you're faced to the north-south and you look at the cloud, you see 30 miles wide. 60 degrees, 60 degrees, 30 miles. That's 30 miles this way, 30 miles this way, 30 miles this way. It's an equilateral triangle. So now, if you happen to be facing to the east or west and you hold out your hands, it's half the sky, because it's 50 miles. So here's a cloud that's this big, but this big, and it's 26 miles away. It's huge. It's huge. Nobody knows how big it is. And Dr. McDonald, when he looked at the cloud, he didn't realize how big it was. He knew it was big from his experience. Anything that would be lit by the twilight sky at an altitude of over 20 miles, which his first estimate was, it's 20-something miles, and it's just way up there. If it's that high and it's that big, this is really special. So let's calculate the volume of the cloud. Now, this is one of the paths I took to validate, not just from one direction, that the cloud couldn't be formed by a Thor-Agena rocket, because the winds are the wrong direction. So I'm going to say, okay, let's just take the case where somehow, unbeknownst to everybody on the planet, the winds got the rocket over there into the right spot, and then suddenly changed and turned, and we got the rocket now going in this other direction. And is the debris enough to actually cause a cloud to form? Well, let's see how big the cloud is and see what it takes to make a cloud that big. So this is another path that you take to develop and establish root cause. Remember, we're trying to eliminate certain possibilities from consideration on the grounds of physics, not on the grounds of our imagination or our emotion or our desire for certain things to be so. You have to be scrupulously honest when you do these kinds of things, because people's lives can depend on you being honest, including your own life. All right. Slide 24. Here we are. The volume of the cloud, he said it was 60 kilometers, that's 60,000 meters, times a width, he said it was 3 to 4 kilometers wide. We're going to use a smaller number. It's conservative. And how thick was the cloud? Well, we really don't know. He never tells us how thick the cloud is. So I'm basing a thickness on the percentage of cloud width. I know that it looks like a cirrus cloud, so it's flat. It's a reasonably flat cloud. And I also know from studies of optical densities what amount of material you have to have in order to make something that you can see. So I did a lot of study on the subject of how much material you have to have in order to see it, because optical density is important. And I hit upon a number. First, I actually made this smaller than what I thought, because I thought the minimum that you would have to have is 500 feet. So here's a cloud that's basically 3 miles wide, or 2 miles wide, and 500 feet thick. So it's really wide, but it's thin. And we can do that. So I'm estimating 152 meters thick, which is 500 feet. And the answer is 27 billion cubic meters. Now, 27 billion cubic meters. But it's in one picture. Now, I've got everybody, where are you going with this? All right, so now, how much does the air weigh that's in that volume? What's the mass of air that exists in the volume? Well, it's simply the volume times the density of the air. Now, we know the density of the air is getting thinner and thinner as we go up. And quite frankly, at this altitude, if you were to open your capsule, if you were to be in this altitude, you would die within minutes. I mean, your blood would boil like that. Because it's only 2.2 millibar. That's, remember, 1,000 millibar is sea level, or standard atmosphere, and you're at 2,000ths of that pressure at this altitude. So, what's the density there? Well, there are tables for density, and I verified those tables by doing my own calculation. Based on the pressure and the constituent parts of the atmosphere, the nitrogen, the oxygen, and so forth, as we discussed this morning, and you take the pressure and calculate from the density of the percent by volume, and you can calculate what the pressure is, or what the density is rather, at that altitude. Or you can look it up and somebody will calculate it for you. I got the same number, so I trust the numbers. So the density of the air is 0.00, big long number, 298041 kilograms per cubic meter. That's the density of the air at that altitude. And you run the number, and it takes, the mass of the air is 81 million kilograms. That's the weight of the air. Now, if you're going to form a cloud, and you see that the cloud is an ice cloud, that means it's a cirrus cloud. It's got the same kind of characteristics as a cloud would have in the cirrus cloud. And a cirrus cloud is the lightest of all clouds. It's got, because it's ice, the formation of the ice into a structure makes it much less dense than water ice as a liquid, or that water would be as a liquid. How many knows the conversion of snow to water, inches of water? What's the ratio? 10 to 1. So if you have a water cloud, like a cumulus cloud or something, the density of the water is going to be a certain amount. If you have an ice cloud, its density is going to be much, much less. And the density of a cirrus cloud is about 1/20th of a gram per cubic meter. So, cubic meter, okay, and it's got a cirrus cloud in it. All of the water that would make up that cirrus cloud would weigh 0.05 grams, or 0.00005 kilograms. It's really light. Now, so if you take that density and multiply it by the volume, the amount of water that's in that cloud is 1.36 million kilograms, or 2.2 million pounds. Now you think that's a lot of water. Well, it is compared to a rocket. But it's not that much compared to what is in the atmosphere all the time. Now, why do I say that the cloud has to be a cirrus cloud? First of all, it's water ice, if it's water. Now, I should stress right here, we're making an assumption that it's water. I have no reason to doubt that it's anything but water, and I'll explain just a little bit more. The temperature and pressure profile at 26 miles, at that 41 kilometer, is such. The temperature, you saw the temperature was going up. Let's go back to slide 20 again. You see the temperature is going up and the pressure is going down. And there's a point where if you went higher than that, the temperature would be too high and the pressure too low, and water would never condense and form or would never make an ice cloud. If you're less than that, you got more pressure and the temperature is lower, then you can form a cloud. Guess what altitude is the maximum altitude that you could possibly form a cloud in this condition? Anybody want to guess? I'll tell you, it's 26 miles. You look at the vapor pressure diagram, and that line that says, here's the temperature going this way and the pressure going this way. Where they cross on that sublimation line, at the temperature at that altitude, and the pressure is right on that line. So it is possible to get a cloud at that altitude if somebody puts enough water up there. Now, it's not going to occur naturally, because we've already seen that the natural water that's in the air, it's not there. But if you somehow put enough water up there, it can form a cloud at that altitude and at that pressure. And that's the highest altitude that it will possibly form. Now, I did that calculation and I came to the conclusion that it had to be this way. And the reason it has to be this way is because water doesn't behave any differently. Just because you put the water here or you put the water over there, it's still water. If I've got the water at a vapor pressure of 2.2 millibar, remember the partial pressure. If the partial pressure of the water is at 2.2 millibar and the temperature is at this temperature, a cirrus cloud will form. Only it'll be in the troposphere, down around, what, 20,000, 30,000 feet. And that's the conditions you would see. But it's got lots of air pressure around it, so the partial pressure of the water would be that low vapor pressure, but it's still enough at that temperature that it would form a cloud. But if you take those same conditions of 2.2 millibar and the temperature of about around 2 or 3 degrees Fahrenheit, something in that ballpark, minus 20 degrees Celsius, and you put that up at a higher altitude, if you give it enough water, it'll still form those same conditions. And so it'll still form the same kind of cloud. You don't get to pick and choose how water behaves. It is what it is. So the cloud that forms at 26 miles based on this crossing of temperature and pressure, that's the highest that the cloud could possibly form in these conditions. You go a little bit higher, it's too hot. If you go even higher, the pressure keeps going down. Now, I will say this, that as you go up and the temperature turns and it starts going back down again, at the very top of the mesosphere, at about 50 miles, it is possible once again to get clouds to condense. They're called noctilucent clouds, nacreous noctilucent clouds, and they're characteristic of altitudes of 50 miles, 80,000 kilometers. And they're seen very, very faint in the afterglow. You never see them in the daytime, but you can see them in the afterglow of night. As the Terminator goes around, those clouds will show up. The folks in the International Space Station get to see them fairly often. And they normally occur up around the polar region, but they could occur elsewhere, possibly. But that's not what we're talking about. This cloud wasn't that high. This cloud was at 26 miles, 41 kilometers. Now, after I did the calculation and I came to this conclusion, I found a paper where Dr. McDonald had done exactly the same calculation and came to exactly the same conclusion. So here's two guys independently doing a calculation based on the physics of this is how stuff works. And he comes to a conclusion and I come to a conclusion, and it's the same conclusion. So you can challenge me on whether I have understanding of everything associated with meteorology. I don't. I'll freely admit that. But I do know something about the properties of water. I boil water for a living. I've been boiling water for a long time. All right. And the free refrigeration guys, they're familiar with these things, these principles of how water behaves when you freeze it and so on and so forth. Frost-free refrigerators, how do they work? You circulate the air to the cooling coil in the back. And the air circulates to the cooling coil is back behind a barrier, so you got a fan, pulls the air around. The cooling coil is the coldest thing, and that's where the ice forms. Well, if the ice forms at the coolest spot, that means where it's warmer, ice doesn't form. That makes it frost-free. And then when the coils build up with enough ice in the back, then you stop, you go through a defrost cycle. You heat up the coils, and the ice melts and drains down the back of the refrigerator through a little hose, down to the bottom to a pan that's in the bottom of the refrigerator. And then you start it back up again, and then the heat that you remove from the refrigerator blows across the fan and evaporates that water and blows it back into the room where the water came from to start with. Did I do okay, brother? That's how they work. Yep. Well, the air has a built-in frost-free refrigerator cycle. And it's called increasing altitude and reducing temperatures, and it freezes out the water so that now the vapor pressure that you have in the upper atmosphere, in the stratosphere, cannot form an ordinary cloud. It simply can't do it. But if you put enough water up there, you can form a cloud. Now, everybody knows that when you send off a rocket, I'm out of time. Brother Luke, I'm sorry. All right, I'll tell you what. Let's, we're going to have to talk about how big the Thor rocket is. And I'm just about there on page 5. I'll tell you what, brother, put up slide 25. And I'm just going to say, is that the root cause? First of all, we're looking for 2 million pounds of water, or 2 million pounds of something, at an altitude where is absolutely the highest altitude that water could possibly form into a cloud, and we're looking for the wind blowing in the correct direction. And we haven't met that criteria so far. Not from this thing, not from this rocket. Even the space shuttle didn't have enough material to do it. And it's 100 times bigger than this rocket. The little things you see way down here at the bottom, those are the solid rocket boosters. This is those are Castor 1 boosters made by the Morton Thiokol Company. They contain 5,200 and something kilograms of material, about 12,000 pounds of solid rocket material. And the claim is on this website that I won't send you to, but the claim is that that little solid rocket booster is what caused that cloud. Yeah. Now I need something north of 2 million pounds to get there. Remember, I estimated the cloud small deliberately. This is the minimum what it takes to make that cloud. So I've got a rocket here that's got, in the booster, that's got 12,000 pounds, and I need 2.2 million. Does anybody see a discrepancy? Now, as far as I know, you folks are the first people, besides the victims at home, who have heard the size of the amount of water that it would take to make that cloud. I've looked on the internet, I've looked everywhere, up way, one way, down the other. I've read all that Dr. McDonald wrote. I could not, on this subject, and I could not find where he ever calculated just how much water does it take to do this. So, not having an answer, I went to the trouble. And the reason I went to the trouble is because if you're trying to do a root cause, you've got to nail it down. You've got to remove all doubt. You can't just say, oh, well, that correlates. That must be it. You're not allowed to do that. I've been in root causes. I'm going to close right here because we'll come back and look at the characteristics of the solid rocket booster and how what it takes to make all this stuff work. Because there was another thing. One of the other things that the brother said was, well, it wasn't water. That's not a water cloud. That's actually the ash from the solid rocket booster, because he knew that water wasn't going to form a cloud at that altitude. Well, it turns out it can if you get enough water up there. It actually can be a water cloud because you meet the temperature and pressure requirements for forming a cloud at that altitude and pressure. So it is possible. If you throw enough water up there, it'll form a cloud. Space shuttle proves it. Space shuttle proves it. Where's that picture? We're going to talk about this. Slide 37. All right, there's a space shuttle launch. This photograph was taken 5 minutes after liftoff, and it's a 10-second exposure. If you look in the left side, you see a little streak of light about that long. That's the space shuttle. It's downrange, and you'll notice this plume of stuff coming out the back of it. That's actually in the thermosphere. Now, he's well above the mesosphere by this time. And that's water vapor from the engine, because the space shuttle main engine was fueled by liquid hydrogen and liquid oxygen. So the only product that it will produce is water. Okay? The top of that plume is an altitude of about right at 26, 27 miles. And that's a combination of water plus all of the combustion products that come from the solid rocket boosters. The SRBs are ejected at an altitude of about 28 miles. And so 5 minutes after the launch, you can see all these different kinds of paths. You notice the squiggly stuff. It's moving this way, and it's got all these, this motion, and that's because of the winds aloft. That's the layers of wind. As you go up the atmosphere, it's pushing this thing to one side. And notice that it kind of settles down when you get up there in the stratosphere, which is normal. Stratosphere is quiet, calm. It's a temperature inversion. The temperature goes up as you go up in higher altitude. Makes it very stable. There's not much convection. And so the other thing to notice is that what you're looking at is 100 times larger than a Thor. Imagine saying that's 1/100th of the amount of material that you would get from that Thor Regina D rocket. And that's what you would have from a Thor. That's a space shuttle. The solid rocket boosters in the space shuttle are, each booster contains 1.1 million pounds of material. So, of solid rocket fuel. So what we're saying, we've got data of how it behaves. Now, 40 minutes from now, go to slide 39. 40 minutes later, here's what the cloud looks like. All the stuff at the bottom, it's gone. It's dissipated, it's been blown away. And then here what you see is all this strange, this back and forth, that's because it's falling. It's heavier than air. When you have a cloud that forms in this manner, it weighs more than the air. There's no buoyancy to hold it up because the density is too low. And so it falls. And as it falls, it gets pushed around by the different layers as the winds blow. So as it falls, you'll see these directions, and it'll get pushed this way and that way. Now, the reason that particular one's important because that's the dawn sky. So you're seeing a cloud illuminated by the sun shooting over the horizon. Well, that's similar to what we saw with the cloud that was taken in Arizona. It was illuminated by the dark sky. You didn't see it, you didn't notice it until the sun went down. And it's like, wow, there it is. So this is STS-131, and it was launched. But I just wanted to show you, this is the way it acts. Now, that is not 26 miles or 30 miles across. Hadn't had time to get there. And furthermore, it's not making a donut shape. It's just being pushed around. And you see these pictures. The characteristic of it is not anything like what you would expect, what we saw in this cloud that appeared in Arizona. It's completely different. So none of the markers are there to say, okay, it was a missile or a rocket. The shape of the cloud, where it was located, the time that it appeared, the density of the material that's required to make it. All of these things point to not a man-made structure or a man-made item. So every avenue that we have taken so far to say, is it root cause? Does a root cause point to something that man has done? In every case, and in every rigorous analysis, we come up not viable. It's simply not there. The numbers aren't there. The direction isn't there. Nothing is there to support and say that that cloud was the result of any man-made activity. Now, you can believe what you want to believe. But if you think man did that, you're living in fantasy. If you think there was a rocket or a plane or a UFO or the Anunnaki or some green man heading on his way to Roswell, yeah, I'm mocking. It's simply not there. It makes me feel religious. I studied this thing. I've studied this for months. Brother Luke, you know I did. He gave me this assignment months ago. I'd already been looking at it. I have notes from a year ago where I was going to talk to a brother about what was going on. On the backside of it, I talked about the cloud. Why? Because if you think that cloud is man-made, you're believing a lie. And you're free to believe a lie. You're free. It's a free country. No one's going to change your conscience. But I wish to God you'd come talk to me first. I could have given you some information that might make you at least stop and think. And is it okay to weep for your brother who is caught in blindness? You don't know what you're doing with your life when you turn down something that's that thoroughly vindicated. Now, all of the things we've said today doesn't prove that God did it. But it sure does prove that man didn't do it. You accept God by faith. And you only know God by faith. You cannot know God by any scientific reasoning. It just simply doesn't work. And I'll repeat again, as I've said many, many times. If you want to have understanding, you must first exercise faith. You will never gain faith by understanding. The faith that comes from this kind of analysis is a faith that is tenuous. It's fragile. It's brittle. That is, if you make some analysis and all of your assumptions and you come up with the point and you say, well, all of these things must be true that I've made my assumptions. Somebody else can come along and might in fact come along and say, oh, Bill, you missed this. Here's what it really is. And that's possible. And in fact, I invite that analysis. I am not afraid of the truth. I have never been afraid of the truth. Now, I will admit that when I started on this study, I had some degree of trepidation. I had some, what am I going to discover? Because you're really heading off into the unknown. And people naturally fear the unknown. You naturally fear what you do not understand. But the more I got into it and the more I saw what was really going on, the more confident I got that our God did something that man was never going to get credit for. He put that cloud in such a location. It's the only location he could have put it. The very highest altitude, which would actually support the making of that cloud. And he put it in such a place with such a shape. And I want to point out something else about the cloud. Let's go back. Well, that's okay. There's something else about it. When you see this cloud and you look at it, the 30-mile dimension is this way. Okay? The 50-mile dimension is this way. So you're actually looking at something, it's closer on the right side and it's farther away on the left side. And it's 50 miles from here to there. And it's 30 miles. So you, to make that picture, to see that cloud in just this way, you had to be standing in just the right spot. Now there's a little thing here that if you want to see God, you got to look at him in just the right way. You look for some other direction. Yeah, you saw this. I don't know. It's a nice big cloud. People did report, universally, people who saw the cloud reported to Dr. McDonald over and over and over. It was the most beautiful cloud they had ever seen in their life. And it's beautiful to me too. So, how many of you driving down the road and it says stop ahead? It's written in the road and the letters look like they're about this tall, right? Because you're driving down the road, you see stop ahead written on the road. Have you ever watched them paint those? The template is about that long. They lay this template down. It's long. It says stop. You know, it's this long thing. But when they lay it down and you look at it driving down the road, it shortens because of the angle, and you see clearly stop ahead. Well, that's the way this cloud is. You're looking at it from an angle. The dimension this way is very long, but when you look at it, it forms perfectly the white-wigged Christ coming down as judge in this age. And why it came when it came? Because it was associated with something God was doing on Sunset Mountain. Man is never going to get credit for that cloud. Try as hard as you can. Hey, you know, we all have tried. Everybody's tried. Dr. McDonald tried. His dying day, he was obsessed with this cloud. How can I figure it out? And to the scientific mind, it's, I don't know how I did it, but it's got to be a rational explanation. There has to be. It just has to be. But to the believer, there's a rational explanation, all right. It's just, you can't. I want to nail down at some point, I haven't looked at the actual physics of the solid rocket booster, because there are a few questions which we have not answered yet. And Brother Luke, we can do this anytime you want. But I actually think I've said everything that I wanted to say. But certainly my conclusions. The chemistry of the solid rocket booster, you can look it up. I'll just say this. The solid rocket material they use is called aluminum. It's aluminum fuel. Powdered aluminum is what they use for fuel. And it is mixed with ammonium perchlorate. And ammonium perchlorate, and then the whole thing is mixed together with a binder, which is polybutadiene rubber. So that's tire rubber, okay? So they mix they mix it up in a vat, and they pour the fuel, the powdered aluminum, very fine powdered aluminum, and the perchlorate and the binder all together, and they make a slurry and they pour it in a mold into the rocket casing through a mold that gives it a form on the inside, and then that solidifies and makes a solid rocket motor. And the reason they do it this way is because this particular fuel is real stable and it's relatively safe. It only goes boom when you light it deliberately. So the fuel has a fairly high specific impulse, which is a way of saying how much energy you can get out of the rocket over a length of time. And the fact that they use aluminum fuel, they could use other materials. They could have used lithium, which would give you a higher one, but lithium's a lot more dangerous. And if you have a lithium fire, well, just ask the poor Tesla owner what happens when his battery turns on, burns up. So anyway, they could use other materials, but they chose aluminum because it's reasonably lightweight and it's very stable. And so here's a solid fuel that's very stable, and you could take it, it'll sit there for years and years, and you light it off, and there it goes. So most of the ICBMs, intercontinental ballistic missiles, are solid rocket fueled now, because you don't have to worry about keeping up with the hypergalls and all the expensive stuff that messes you up. So anyway, so that's the solid rocket fuel. The same solid rocket fuel that's used in the space shuttle was used in this Castor 1 booster for this thrust augmented Thor missile. And the technology is fairly old. It was actually invented back in the first part of the last century. And so it's reliable, it works. The products from that combustion are all heavier than air, except for water. And carbon dioxide. Carbon dioxide's heavier than air. Carbon dioxide's one of the products, but it's a gas, and so it just mixes. It's fine. But water has the property of this condensation, of this ability to make a cloud after it. And the other products are aluminum oxide, which is sandpaper. Same stuff that's in sandpaper. And the other is aluminum chloride, and all of those materials are much heavier than air. Aluminum oxide is 3.5 times heavier than air. Aluminum chloride is 4.5 times heavier than air. And when it agglomerates big enough to where you can see it, the agglomeration of that material to make any kind of a cloud that way is simply too heavy to stay in the air. It just falls out. And so it won't be suspended for 3.5 hours at 44. And plus, We still have to have enough material to make a cloud that's 30 miles across and 50 miles long. And you can't get that out of that little bit of material. The fact that God is a creator is not accepted by most of the world, but for us it's plain. We have actually seen the results of God's creation in this day through the ministry of a vindicated prophet of God. And we say that word vindicated, we mean that God has removed all doubt. And the reason he has done so is to declare his glory. He is actually declaring that he himself is a creator, and he has proved that it is so. And we don't accept those things lightly. We accept those things soberly. We don't. I for one don't believe what I believe just because it's just a nice thing to do. Quite frankly, it's difficult to face the world when they don't believe. And I've been in many arguments with people. I repent of that. I'm sorry. I don't mean to argue, but when I first became a Christian and I had the truth, and I thought, my goodness, everybody ought to see this. Why can't anybody stop this? It's clear. This is the scripture. I mean, it's just, wow, why can't anybody believe it? And then you find out, no, those people won't believe it. So anyway, we come to find out, Brother Branham talked about this war, and I really appreciate Brother Luke's message this morning. It was right to the point. I told Brother Luke, I said, I'm so glad you preached that this morning, because now I don't have to mention it. But the war between the mind and the heart is part of life. It is a part of what we go through. And Brother Branham tells us that. He says we reason with our mind, but the heart doesn't reason. That's right. The heart just believes. We look with our eyes, but we see with our heart. So you take something complicated, you say, I don't see it. You mean you don't understand it. But your understanding comes from your heart. You have understanding. Now, many times, I know all Christians know this, that people will think, well, it just can't happen. But yet in my heart, there's something that tells me that it is going to happen. Did you ever have that experience, you Christians? Amen. Sure you have. That's the inside man thinking. It casts down reasons. It doesn't have anything to do with reasoning, because with God, words should not be reasoned. We cannot reason out God. God is never known by science. Never is. God is known, God never is God known by mental powers. God is known only by faith. Knowledge will never get a man to God. Knowledge takes him away from God. Now, with all of the emphasis that we have on education, and I, for one, am a product of that. My father was a college professor. He taught civil engineering at Clemson University. I grew up in the college town. I grew up among academics. I married a woman who also grew up among academics. Her parents were both college professors, and so who you marry reflects your own character. And so I guess God knew that we deserved each other. But she's a wonderful woman, and I appreciate her putting up with me so much. It helps to have a little sense of humor sometimes to make things go better. But in growing up in this academic world, I, for one, have had to fight those mental battles about whether truth is truth, and faith, muster up faith and whatnot. You don't have to muster up faith. Faith just is. You just believe, see. So I come to find out, after many years, as I gain more wisdom and gain more understanding of the way that God works, that the first time I heard this message, the first time I heard Brother Branham speak on tape, something on the inside of me said, that's what I've been looking for all my life. And it was true. And that was that, I find out, is actually an expression of faith, because you recognize a voice of truth. Now, many people want to say, well, he wasn't true. Well, you believe what you want. But when did you ever have thus saith the Lord? When did you ever stand before groups of men and declare him as ever he did, and God back up his words? When did you ever tell someone where they came from, what their problems were? When did you ever foresee in visions things were to happen, and it happened word by word? So Brother Branham's gift took him places that you and I will never go. And God told him when he was just a child, don't ever smoke or drink or defile your body in any way, because I have a work for you to do when you get older. And so Brother Branham, as a child, not understanding anything and not knowing God at all, still God spoke to him and warned him of how he should live his life. One of the reasons that you, as a minister, as a deacon, as anyone, as a Christian, you want to maintain a transparent life is because people are watching, and you are representing someone who is much greater than us. So, to get back into our subject, we last week, right at the end, I actually tried to pile all of this stuff together, and y'all probably didn't notice too much that, I was piling stuff all together, but I was. And so just to let you know, I knew that I was. So, but we actually have a number of things to consider still. And one of the things is people have claimed or postulated that this rocket, which was fired from Vandenberg Air Force Base, was the cause of that cloud. And people have latched onto that because, well, it's the only thing they can latch onto. There is no other rational explanation. And this was first offered, actually, I'm trying to find my notes. Here we go. This was actually first postulated by Dr. McDonald. He sent out, when the cloud appeared, Dr. McDonald's professor of atmospheric physics at University of Arizona at Tucson, and he was a very smart man. He also understood the subject very well, and he knew what would and would not work based on the laws of physics, which are the same laws of physics that we study today and that we know today. They have not changed. And the things which he expressed in his studies are the same things that we would express today if you were taking up that subject. He wrote textbooks on it. He was an authority on the subject. And he knew that he could not make that rocket work. He never, in all of his studies, he could never make the connection from the rocket at Vandenberg Air Force Base to the cloud that appeared over Flagstaff, Arizona. Through any laws of physics, that he knew it wouldn't work. But it was the only thing he had, because it was the only thing that correlated. And the correlation, of course, was this rocket was fired off at Vandenberg Air Force Base 3.5 hours before the cloud appeared. It's after sunset, or right at sunset. Now, somebody mentioned they didn't know where Vandenberg Air Force Base. Brother Malachi, can you pull up that website again? I just want to show you. This is earth.nullschool.net. We'll look and see what the winds are doing today. We looked at them last week, and it's basically, last week it was blowing in the right direction, maybe, but it wasn't fast enough. It didn't have enough velocity. So there's all kinds of things that have to be met. I mean, you don't. Brother Branham explained it this way: you're firing a rifle, and you're going to fire the bullet towards the target, and you got to get the sights lined up exactly on the target, and you have to account for the fall of the bullet as it travels through the air, and you have to if there's a puff of wind comes along and just puffs it off a little bit, it'll miss the target. So this is simple ballistics. Simple ballistics is, there's some equations you can write to describe it, but it's all perfectly ballistics, and it's perfectly predictable. The M1 Abrams tank, they've got the ballistics of that gun so well predicted. They can aim this thing while they're going down there, fire three shells, boom, 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 and the ballistics will make those shells all fire and land in the same spot. And they can do that while they're moving down 40 miles an hour across the earth, you know, doing all this kind of stuff. So it's ballistics. It's perfectly predictable. Well, this is perfectly predictable as well. All right, now, Vandenberg Air Force Base is go down, 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 down. A little bit more, right there. Okay, that little crook in the coast of California, pull it up. You grab it and pull it up. Yeah, there you go. Okay. Now, that's where Vandenberg Air Force Base is. That's, it's right off the coast of California. When they want to send rockets into regular Earth orbit, like the space shuttle or like the space station that's up there, they fire the rockets off from Cape Canaveral in Florida. Because the Earth spinning, which way is it spinning? Let's see, this is north, so we're spinning this way. So the Earth spinning this way gives you a little velocity boost of about 1,000 miles an hour. So you've already got, to get into orbit, which you got to go 17,000 miles an hour to get into orbit, then you've already got a boost going that way. So they fire them off, and it's to the south, so it's got some velocity and so forth. So that's why they do that. Now, if you want to send them off into polar orbit, that is a satellite that goes around the poles north to south, which they do if you want to fire off spy satellites, because you want them to spy on Russia. So they fire them off from Vandenberg Air Force Base, and they fire them off across the Pacific Ocean. If they have a problem with a rocket and it blows up, it lands in the ocean, no harm done. And all your secret stuff has disappeared too. So that's where it is. Now, over to the right, let's see, 35 degrees, and a little bit more, a little bit more, a little bit more. I go down just a hair, right about there. You poke there. Okay, so now we're at approximately where Flagstaff, Arizona is. You measure that distance from Vandenberg Air Force Base to there, it's 500 plus miles. And if you fire a rocket off and it's heading out towards the sea and then they blow it up, then it's going to be about a little over 510, 520 miles, something like that. That's the distance. Now, if there's any rocket debris that gets from there to there, the wind has to blow over 135 miles an hour at the altitude where the rocket or the cloud would appear. So let's go up to our altitude again, Brother Malachi, and let's look at the 10 millibar level, which shows you that the winds are blowing almost from the right direction, a little bit, just 5 degrees off. You know 5 degrees off is enough to put you miles away from where you're supposed to be. So, I mean, it has to be exactly the right direction. 265 degrees, that's the angle. And then it has to get there to 135 miles an hour. Well, this is 35 kilometers per hour, which is about 20 miles an hour. So the winds at that altitude won't get you where you need to be in the right amount of time. And we pointed out, and Dr. McDonald pointed out, they took soundings of the winds at the altitude, and they weren't fast enough. He said they were a bit too slow, like 95 miles an hour, 90 something. Well, that is too slow. It won't get you there. And then we also have the eyewitness testimony, which said the cloud was moving from the northwest towards the southeast. And in moving that direction, we also know that these patterns, you'll notice it's very broad. This is like when you get these patterns. All right, Malachi, pull out so we can see a larger part of the earth. If you can scroll out. There you go. Yeah, keep going. Keep going. Keep going. Okay, here's the earth. And now you see the winds. The wind patterns up there, you see where it's purplish and whitish and so forth. Those winds are fast enough. That's where it's 240, 270 kilometers an hour. And that's about the speed you have to get the winds to go from Vandenberg to Flagstaff. And you'll notice these patterns the way they are. There's a polar pattern. There's a cell down below. That's the tropical cell. And there's actually 3 circulation patterns that dominate the Earth. You've got the Hadley cell, the midcontinent cell, and the polar cell. And those are all cells where the airflow, it rises up because it's hot, and that heat is transported and then dumped into the lower, dumped down, and so it helps warm parts of the Earth that don't get enough sun to be that warm. So that's part of what makes the temperatures across the Earth as uniform as they are these circulation patterns. So you can see that in this area right around the 35-degree latitude, which is where we are, we're sort of in a no man's land for these cells. Sometimes they drop down and you get high velocity winds, and sometimes they go the other way. And about 6 months from now, if you look at those winds, they will be going just as hard as they can go easterlies. They'll be blowing away from the coast just as hard as they can go, just like the ones down below do. So that's the patterns that happen in the atmosphere and so forth. But we see from the winds that you can't get the debris from the rocket over Flagstaff. Now, that's one grounds right there. You just can't get there from here. We also know, then we studied, that the volume of this cloud is huge. And we calculated what it was and gave a limit, a minimum of, 27 billion cubic meters, with a mass of the cloud to be, I said 2.2 million pounds, but I was wrong. And nobody corrected my math for some reason. Okay. Malachi, if you'll pull up the slide 24. We're done with this. We're done. I just want to show you where Vandenberg Air Force Base was so people would know what we're talking about. And I think it's slide 24. Yeah, there it is. It's 1.37 million kilograms is 3 million pounds, not 2.2 million. The reason I got 2.2 on my mind is because the solid rocket boosters, the 2 of them on the space shuttle, are 2.2 million pounds of fuel. All right, now I want to continue on. And remember, I'm approaching this, and we are approaching this from the standpoint of root cause. Root cause is a powerful technique for finding or connecting an initiating event to a final event. And we ask the question, can this rocket be the root cause? So it's the next slide, I believe. There it is. Is that the root cause? Now, the thrust augmented Thor. First of all, the satellite that they're sending into orbit with this rocket is a spy satellite. It's called a Corona satellite. It had a specially developed or specially prepared photographic film in it that the Kodak company put together. And that film was a very high resolution, very fine-grained film, and it also could withstand a lot of radiation, and it could withstand these extreme temperatures that it had to go through. So they would fire this missile off, and you notice at the capsule up the top there has got a bunch of windows in it. That's where the cameras are behind those, and they take the photographs. So this is called an Agena D. The upper stage is called an Agena. They had different names, mostly Greek, just because, I don't know why, but they did. And so The lower part of it is a Thor, which was actually designed as an intercontinental ballistic missile originally. And then at the bottom you see two, but there's three, of the little things right there on the end. Those are the solid rocket boosters, which are the augmenting thrust to that Thor rocket. So it was called a TAT, thrust augmented Thor, Agena D. That was what it was. They would fire these things off, again, towards the south in a polar orbit. They would orbit around the Earth, and every time they go over the Soviet Union, they would orient the pictures and would take photos. And it would be a continuous stream of photos. And then, as they would go around again and take more photos. And they kept taking photos till they covered all of the areas that they were interested in taking the photos. They would then deorbit the rocket. They still had some fuel, still had the Agena D attached to it, and they would retro thrust and deorbit. They would put out parachutes, and the satellite would gently come down to Earth somewhere over Nevada, if they were doing it right. And they would take a flying boxcar, C-119, and they would draw a hook out the back of this C-119, and they would grab this satellite in midair. How many's ever seen photos of that? Somebody's nodding there. Okay, somebody has actually seen the photos. And actually what, so they'll grab this, they got like a fish hook, big long drogue hook out the back of the C-119. They would grab the satellite in midair, grab the parachute, and they would pull it up into the back of the boxcar, and then they would take the satellite and immediately begin to remove the film canister from it while they're still flying, land on Earth, get back straight back to the processing place, and rush that film to development. And then our military agencies and spy people and whoever it is that are really, really good would pore over these photographs and determine what the Russians were doing. President Eisenhower authorized all this, and it was done with, all of this was done under military slush funds, and so it was all supposed to be secret. And in fact it was. These were top secret. Not the fact that they fired a missile off. I mean, how are you going to hide that? You know, here's a rocket, you know, that everybody in Los Angeles up and down the coast, hey, they fired off another rocket. I wonder what they're doing. I don't know. Probably trying to find out what the Russians are doing. So, and that's what they were doing. And this was actually very important to get that intelligence because we're in the middle of the Cold War. And this was right after Korea, or maybe, yeah, just right after. It's right along about that time. And so they're firing these rockets off because they want to know if they can back up any of the ground information they're getting, or are they getting information that's good, or are they being fed a bunch of lies or whatever in the measures, countermeasures, and so forth that goes on with espionage. You know, they could ask the prophet, I guess, but, you know, they don't. You know, there was a prophet in the Old Testament who told the king, he said, hey, watch out, you know, king of Syria, he's going to come over here and he's going to do such. How come they always know what I'm wanting to do here? So at this time, the United States is trying to validate the information they're getting about Russia, and so in doing that validation, they're actually able to say, yep, they're this far along, or no, that's a bunch of hopefulness on their part. They're really not that far along. And they actually were able to determine that although the Russians had a great deal of technology, they were advanced technologically, they didn't have a lot of it. And so it helped diffuse some of the political situation, which we are very thankful for. Because we're here. Now, so that's what that thrust augmented Thor. Okay, so let's give some dimensions on this Thor. Remember, Professor McDonald is the one who first, in fact, I'll read what he said in this paper in Weatherwise, which was in June 4th, 1963, is when this was published. And he talked about the cloud. He said, what is the cloud? What is it? I said, I'm still trying to answer that. It was far above the upper limit of contrail formation. We talked about that last week. There were no X-15 flights. There's no Nevada test flights. There's no jets that are up there. They can't get that high anyway. And so he said the Thor booster of a military satellite launch was detonated at 44 kilometers at 13:52 Pacific Standard Time, almost directly over Vandenberg Air Force Base. To account for a drift of 510 miles to Flagstaff and time to have lowered the jaws of Flagstaffians looking straight up at 1840 Mountain Standard Time calls for a mean drift speed of 135 miles an hour. So Dr. McDonald was the first one that identified this as a possibility. So the people want to say today, oh, well, that's what it was. He wants to say what it is. He wanted that to be the truth. There's no question that Dr. McDonald wanted this to be the answer. But he had enough scientific integrity about him, enough scholastic integrity that he would not join dots where dots did not exist. He would not make bold statements where he did not have data to corroborate what he was postulating. Now that's a good scientist. That's what we all must do. If you're going to get to the truth in a root cause, you're not allowed to speculate and make stuff up. Now, it's okay to postulate. It's okay to say, well, I wonder if it could be yada, yada, yada. And typically you'll get in a group, and a group of people will get together, and people will throw out ideas. And then I'm going to have to take my coat off. This thing is grabbing back there. So, but what you do then, after you've got an idea, is as ideas are presented, then you begin to confirm or reject one by one on the basis of physics, on the basis of what's possible. And so Dr. McDonald, he wanted it to be there, but he couldn't make it work. And my understanding is he never was able to make it work, and he never claimed that this was it. But some people are claiming that it is. And I even saw one claim that said, oh yeah, it wasn't water, it was the debris from the solid rocket booster that made that cloud. And so, since someone made that statement, I figured somebody makes a statement, you ought to be able to connect the dots if that's a fact, if that's true. Well, we can't connect the dots from the wind, but we also want to talk now about what this missile is made of. So in slide 26, the thrust augmented Thor has basically there's three parts to it. There's a main rocket is 110,000 pounds of kerosene and liquid oxygen fuel. And then the second stage, which is the one is the Agena D, is 32,850 pounds of nitric acid and UDMH, which is unsymmetrical dimethylhydrazine. That sounds like a mouthful, and I had to practice that. But that's what's called a hypergolic fuel. Hypergolic is, if you can go on YouTube if you want, it's kind of interesting. You take the hypergolic fuel, like the hydrazine, and you just barely mix it with one of the oxidants, and it instantly fires. No ignition required. It will just simply fire off. And so they use this for thrusters in outer space. So you have a tank of the hydrazine and a tank of the oxidant, and all you do, and they're pressurized, and all you do is just open two solenoid valves and mix them together in the nozzle, and boom, instantly you've got thrust. So this is it's hypergolic, it requires no ignition. the last three components here was the solid rocket boosters, and this is the one that's under consideration. This was a Castor 1 booster made by Thiokol Company, the same company that made the solid rocket boosters for the space shuttle. And the chemicals in those boosters were essentially the same. But those boosters, now they didn't tell me how big they were. What I did was I took the dimensions of the thing. They did tell me how the physical dimensions of it. And you figure, okay, here's the physical dimension of it. And they're going to use 90, and you calculate the volume. And then you figure that they're going to use 90% of that volume to put fuel in it, because you have to have a space in there so it can actually form a rocket. So it's about 90%. And so I did the calculations, and I came up with about 5,400 kilograms of this solid rocket material, which is about 12,000 pounds. There's 3 of them, so that's 36,000 pounds total. Now, they said it was the solid rocket booster that did it. So, what is a solid rocket booster fuel? The fuel is, next slide, the fuel is aluminum, powdered aluminum. And it's powdered, I mean, very, very fine. If you threw it in the air, it would drift. It's extremely fine powder. And then they would mix that with ammonium perchlorate, and they would use basically tire rubber to stick it all together, polybutene rubber. The product of this is actually alumina, which is aluminum oxide, aluminum chloride, water, nitrogen, and carbon dioxide, just from those reactions. Go to the next slide. Here's the chemical reaction that's going forth. Now, the reason I want to point this out is because I didn't do the calculation for the polybutene. It's simply carbon and hydrogen, and so it's going to form water and carbon dioxide. That's the result of that. But these people said, okay, we dismissed the water. It's got to be the other part. So the other part is the aluminum oxide, which is 4 molecules, or 4 moles. You get 2 moles of aluminum chloride, you get 12 moles of water and 3 moles of nitrogen gas. And that's the result of that combustion. Now, how many remembers our studies on atomic weights? Some of you remember. Okay. So the next slide will show you the atomic weights of these things. So you look at the molar weight, and what you'll discover is, of course, the water has a molar weight of 18, the nitrogen's 28, the CO2 is 48, but the aluminum oxide is 102 grams per mole. It is much heavier than air. It's 3.5 times as heavy as air. And the aluminum chloride is even worse. It's 4.5 times as heavy as air. So when you're talking about particles that are going to somehow make it 510 miles and hang together in a clump and then spread out over 26 miles or 30 miles and then about 30 by 50 miles and have enough density to make a cloud that you can see, and it's heavier than air, by the way, and I personally think you can't get there from here. Amen. That's really what it amounts. Okay, so the water is the lightest of all of the products. The nitrogen and the CO2 are gases. The aluminum products are all solid, but they're all heavier than air. Now, we come into another little piece of this, because how much of this aluminum, if you were to get these aluminum products in a condition where you could see them, they have to be a certain minimum size. It turns out when you combust these things out the back of an exhaust, there's a range of physical particle sizes that appears as a result of the combustion. And the range of particle sizes is from 0.5 micron up to over 400 microns. Micron being 1/millionth of an inch. Now, in order to be seen, the particles have to be a minimum of about 1 micron diameter, because if it's not that big, it doesn't reflect light. So you got the wavelength of light that you have to worry about. And I'm sorry I'm putting everybody to sleep, but this is a boring subject, I know, but I got to cover it. Now, so you look at the particle sizes, and it turns out that only about 2, maybe up to say 5% of the products are in a particle range that would even potentially be suspended in the air, not because it's still always heavier than air, but if you've got an updraft or some kind of turbulence, you actually can carry particles that are heavier than air as a part of the conversion of kinetic to potential energy through the fluid process, fluid dynamics. Well, that follows a 3/2 square law, because the velocities are a square term, but the mass is a cube term. So as the particles get bigger, you get less and less able to do that. And by the time the particles get up to over 10 microns, they will not stay in the air, period. It'll fall right out, especially at these altitudes where the air is so thin. The air is very thin. You remember the density is very low, and the air pressure is only 2.2 millibar at that level. So we don't have enough air to even, it would be hard to keep this stuff suspended down here at the low levels where we have lots of air and lots of turbulence. It's impossible to keep it suspended at 26 miles altitude. It won't stay up there. It's heavier than air. The water vapor will stay up there because it's lighter than air. The vapor of water can stay suspended because it's lighter than air. It's 18 grams per mole, but once it condenses, once you turn it into the solid, the particles that you can see, it is now heavier than air. And so it's got to start coming down. Now, I hope I put this thing, but by the time you get to seeing what material you would have left after you've burnt all of this material and you have these products left, it's only a fraction of a percent or a fraction of the total that could even possibly turn into a cloud that you could see. And then from that fraction, do you have enough material that could, with particle sizes big enough, to actually make a cloud that's that huge? And the short answer is no. The longer answer is what we just described. I mean, I said all this to say that you go through the process of trying to look at what it takes to make a cloud, and I did studies on this. I said, all right, well, how much density of material do you have to make it visible? And the answer is you've got to have particles that, first of all, are big enough that they'll reflect light so that you can see them. That means they've got to be over a micron size, and they have to be actually a little bigger than that. And then you look at the size of, say, the materials that go in, and that's just to make a haze. And if you want to make a definitive cloud, it's got to be even denser than that. And that's why when you look at a cirrus cloud, sometimes it'll be a haze, and then here comes a jet flying along, and then that haze turns into a contrail and actually becomes dense. And now you can really see it because the airplane added a little moisture to it and also added cloud condensation nuclei. Glad added something that the water could build itself around and make a cloud. And so now you see a cloud going across there, and we call it a contrail. So that's what's going on. Now, so in the rocket plume, next slide, brother, only a small fraction of the rocket exhaust exists at an altitude range of the cloud. Now, when you fire off a rocket, sitting on the launch pad, it's all of those masses that we just described. Once you fire it off, you immediately begin to burn material and blow it out the back. And so as it goes up in altitude, you have the rocket is not only producing thrust to make it accelerate, but it is also losing mass. And so what you have left is able to go faster. It's something similar to when you blow up the little balloon and you let go of it. Now, it's not exactly this, but I just want to give you the idea. It starts off kind of slow. Of course, there's no direction to it. It's just going everywhere. This is the fun part, right? You don't know where it's going to go. So, but it fires off, and then as it consumes and gets smaller, the air resistance goes down, and the little guy gets faster and faster. So it goes, and then falls out of the sky, right? Everybody see that? How many kids know what I'm talking about? Okay? You even got some smiles down here. This is great. So here's a rocket does something. Now, it doesn't go every which way. You have to blow it up if it does. But it does something similar in that as it fires, it's spewing out huge quantities of material at very, very high rate. And that also is now stuff you don't have to accelerate. So it gets lighter as it goes. It turns out that typically on one of these rockets that you're going to put into orbit, by the time you get to this altitude of 26 miles, you have expended 2/3 of the rocket material. The rocket, 2/3 of it has already been expended. And so the next 1/3, of course, now you're not accelerating that 2/3, and so you can shoot it on off, and most of the energy that you put into a rocket is not to get it up to altitude. Most of the energy is to get it up to speed. So, you want to get an altitude of like 50 miles or 60 miles or whatever it is. You want to get it in outer space, low Earth orbit. In the case of these Corona satellites, they don't want them in a high orbit. They want to get them down where they can get really good photographs. So it's a low Earth orbit. But you got to make it go fast enough that it'll stay in orbit. Anybody understand how that works? You've had it all explained to you, but here we go again. So putting something in orbit, an object that's in orbit is literally falling around the Earth. You throw a rock, you'll throw a rock, you don't throw rocks. Throw rocks. You throw a rock, it has this arc. Or you shoot a gun, a lot more powerful. It makes an arc. And if you keep raising the angle, eventually you get a point where the maximum distance you can get out of that. Well, let's suppose you have a gun that you can continually put energy behind. So as it fires, it actually goes around the curvature of the Earth, because the Earth is a ball and it's curved. And so you fire that farther and farther along the curvature of the Earth until finally you fire it so fast that it doesn't hit the Earth anymore. That's orbit. That's all there is to it. You fire the bullet fast enough, it simply falls around the Earth. It never hits, never lands. And that's what you do with a rocket. So most of the energy of the rocket isn't to get it up high, it's to get it go fast. But it turns out about 2/3 of the material is eat up or used up. In the case of a solid rocket booster, it's all used up. So if we look at that plume again, you remember last Sunday night, it was very impressive. Slide 37, let's just jump ahead. All right, most of that rocket plume that you see there, that's from the solid rocket booster, from the space shuttle. And you notice it quits. And actually quits up there around 28 miles. And the reason it's that high is because that's where the boosters run out of fuel. And so they jettison them. And then you'll notice that there's an area between where the space shuttle is, the streak of light, and where the solid rocket booster, there's this big exclusion zone. That's the mesosphere. There's the water is being produced by the space shuttle, but it dissipates rapidly because of the temperature and pressures are so low. And so you don't form a cloud. And in fact, you can see that the exhaust from the space shuttle is pluming out up there in the mesosphere, and it is rapidly dissipating because it's of extreme low pressure. That exhaust, which is pure water, it's hydrogen and oxygen, liquid oxygen being mixed together to form water. That is only going to last as long as that internal vapor pressure can be collected in an area. And gradually it'll dissipate, and it's all gone. Now, ultimately, at an altitude of about 50 miles, the temperature at the top of the mesosphere gets so cold that you actually can start forming water clouds again. They're called nacreous clouds or noctilucent clouds, and they are due primarily to man firing rockets up there, then putting water up in the upper atmosphere. Got to go somewhere. That's where it goes. So, all right, so let's go back to slide 31. All right, so here it is. Could the aluminum oxide and aluminum chloride, which are solids, could they possibly be what made that cloud? And the answer would be no. Because most of it, first of all, it's a tiny fraction of the total. Third, it's heavier than air. And so there's not enough of the material available to make a cloud of even small size, much less a cloud of huge size. And so we simply don't have enough material there. Even if it were to get blown in the right direction, even if it weren't scattered in a chaotic process that would make it not be gathered together in a picture or in an oval or a torus, you couldn't get it to do that. Now, even if you have one booster that failed to fire, which is 5,200 pounds, or excuse me, 5,200 kilograms, 12,000 pounds, they said that the failure of this rocket was one of the boosters failed to fire. So if one of the boosters failed to fire, it throws the rocket now off axis. It's no longer symmetrical in the thrust, and so it goes off in a direction it's not supposed to go. So the range safety officer says, we are way off course. The missile is dangerous, the rocket is dangerous, and he pushes the destruct button and he destroys the missile. And when he destroyed the missile, it was at an altitude of 44 kilometers, which is above where the cloud appeared. It's higher by a mile, roughly, maybe two, something in that ballpark. So the rocket that's destroyed, let's just say it failed to fire. Now I've got 12,000 pounds of stuff. 12,000 pounds of solid rocket fuel that's going to get destroyed at that altitude. Is 12,000 pounds of this fuel able to do it? Is it able to form this cloud? First of all, if it doesn't ignite, then it's a bunch of rubberized, conglomerated stuff that simply breaks apart and falls into the ocean. It's heavy. It's way, way heavier than air. It cannot be suspended in the air. If it ignites, though, and it burns up, now it's not being ignited in a rocket. It's being ignited in some kind of a broken up material. It's been shattered. And so now the fuel burns in free air, and it doesn't have the nozzles to force it into the fine particulates that are the result usually of this kind of combustion. And so what you wind up with is a bunch of very large particles. And the particles that are a result of that kind of an explosion are even bigger. They agglomerate to something that's even bigger than what you would have if it went out the nozzle, which has been characterized as most of that stuff is in the 200 micron range. And so the answer is, you're not going to get any material from that explosion other than water vapor that would possibly be carried by the air. Because all of the aluminum products are way heavier than air, and it simply won't stay up there. Now, you could invoke magic, but we're not allowed to do that. This is a physics class. Okay? So that's why we come to the conclusion that if you turned all of this rocket's mass into the mass of that cloud, you're still only 5%, maybe 6%. If you turn all of it in, you would still come way short of what was required to make a cloud. And if it was the water that came from that launch, you've only got 3% of what it takes to make the cloud. So, the wind's blowing the wrong direction. The rocket doesn't produce enough material. It can't get there. Just the products that would result from that explosion or from any kind of combustion of this rocket, none of those products, except water, could possibly form a cloud at that altitude. And if that were true, we don't have enough by a factor of 100 over 3. We're that far short. We got 3.5. We got a little, about a third of a tenth of a percent of what's required, or a third of 10%. We've got 3% of what's required to make a cloud that actually appeared. So I'm going to say that if you think that rocket made that cloud, you've got a lot more faith than I've got. It's easier for me to believe Hebrews 11 verse 3 than it is for you to turn a thrust-augmented Thor rocket into a cloud over Flagstaff, Arizona. Under any circumstances. Now, let's do some validations. There was all kinds of questions. When you study something like this, anytime you approach a problem like this, I'm just going to throw this out, from an academic standpoint, you're given a problem. You give a problem in school, and the problem is always to teach you something about a principle or a process. But if you do a problem in real life, it's not to teach you anything, it's to actually solve a problem. Which means you have to approach it from okay, here's the end point. I've got to show something happened over here. What do I have to make that happen? And so you start building all of the criteria that have to be met. Well, we did that. We said the cloud is a certain size, it's at a certain altitude, it's got to meet certain requirements. Is it possible, or what does it take to make the cloud? And we figured out, if you're going to make a cloud and it looks like water, Dr. McDonald thought it was water. He never thought it was aluminum oxide or aluminum chloride. He said, that's water. That looks just like a cirrus cloud. And it does. It looks exactly like a cirrus cloud. That's the same kind of stuff that you'd find. The only thing of it is, it's in a very, very peculiar shape. And I don't mean peculiar as odd. I mean it's unprecedented. You don't find clouds like that. You just don't. Not at that height. Not at that location. Not at that time. Now, it's very odd, the timing of the cloud. It's very odd how long it existed in the sky. It's very odd that the cloud even existed at all. All of those are strange things. So, it's water. Someone will tell you, well, it's not water. He's wrong. It's water. The fact that it appeared at the maximum altitude that water clouds could form is important. Because the cloud, once a cloud forms at this altitude, it is now heavier than air. Remember, water vapor is lighter than air. But once it condenses, it now forms a substance of water ice, and that's got a density that's heavier than air. So this cloud is going, once it forms, it's actually going to be descending. It's actually going to start coming down. Now, the altitude of the cloud, when it was first seen, when it first appeared, from the photographic evidence, it was 26 miles high, 41, 42 kilometers. When it went dark, that is when and the reason it went dark is because the sun, it's rotating, the cloud and all is rotating with the earth. Okay, so it's rotating. And the sun is over here shining. And so the shadow of the earth eventually comes to a place where the shadow, this cloud which is rotating around, now gets shadowed. Everybody see that? Okay? So once it gets shadowed, what altitude is it? Well, Dr. McDonald figured that out. He said based on the geometry of this thing and when it went dark, at the time that it went dark, it was only about 30,000 kilometers, or maybe even lower. He gave one number, said 24,000 kilometers. That's down here in the, at the, almost to the troposphere, and you get to that. So the cloud started off high, now it's heavier than air, and now it's descending. Well, it's physics. This is one reason why it was 26 miles high, but now it's descending. Well, how did it get there at that moment in time to be illuminated exactly when it would be illuminated? We don't know where the water came from. It certainly didn't come from California. And so the cloud, once it forms, it's heavier than air, and now it's descending. It did not stay at 26 miles. It descended, and when the cloud descended, it's also moving at 95, a little less than 95 miles an hour from the northwest towards the southeast, which is the same direction that Brother Branham would be standing when the angels appeared to him. Now, there's a lot of details about what Brother Branham said about this cloud. And I don't want to get into that. I want to talk about just the cloud. So we're almost done. I think we are. Yes, we're almost done. So let's go to slide 33. I want to skip over this thing about... Oh, no, actually I do. Let's go to 32. Here's some literature. First of all, if you go to Wikipedia, and this is the wrong place... You kids are not allowed to depend on anything you read in Wikipedia. You understand that? All right, the reason is because anybody can change it. It's unreliable information. However, the references that they give are good references. Go there. So take Wikipedia, go down to the bottom, find the references, go look up the references. That's the documentation that won't change. You see, if you can get a hold of that. That's how I found all of Dr. McDonald's papers. Princeton University, you look him up in Wikipedia, and down at the bottom they give, here's a link that goes to Princeton, and you go find all his papers. And that's good. So that's fine. But here's I just from the article, twilight phenomena. This was a twilight phenomena. It's a noctilucent cloud. It was a cloud, what they call an aqueous cloud. Water exhaust particles from a missile or rocket propellant left in the vapor trail of a launch vehicle condenses, freezes, and then expands in the less dense upper atmosphere. And we saw the picture of that from the space shuttle. The exhaust plume may also take on a corkscrew appearance that is whipped around by upper level wind currents. Typically seen, I want you to get the timing here, 2 to 3 minutes after a launch has occurred. Depending on weather conditions, it could remain in the sky for up to half an hour before dispersing. Think about 3.5 hours. To date, no malfunctioning missile or rocket has been known to create the phenomenon. On the rare occasions when a missile or rocket does malfunction, it is destroyed by the range safety officer before reaching the altitudes where twilight phenomena can occur. Now that was actually taken from a government publication. Now the reason you say that, this is not the only time a rocket's been destroyed. Rockets, but usually when they're destroyed, they're close to the ground. But here was a rocket that was destroyed at an altitude that, had the sun been shining up there at the time and the timing had been right, it would have created probably this noctilucent cloud. But it wouldn't have looked like that cloud. It would have looked like something else. And in fact, we got pictures of where they blow things up or where the exhaust plume goes, and the plumes, they don't look anything like that. What they look like makes sense from a plume that's, okay, it's condensed, now it's heavier than air, it falls. As it falls, it goes through the wind, gets blown around all these different directions. And so you wind up with all of these crazy looking shapes and stuff. They don't look like, they look like Hydra. They don't look like that. They don't look like that cloud, never do. So, I mean, just on the basis. So, according to the dispersal rules of what you've seen with rockets, in the 3.5 hours it would take between the rocket destroyed to the cloud appearing in Flagstaff, it simply would disperse. It would be no way, it is not possible for that rocket, in any reasonable analysis, to have anything to do with that cloud. All right, now, 33, validation. Okay, when you do root cause, you need to validate. You make assumptions, you got to go validate your assumptions. If you think you're going to, if you've got to have an iron case, a closed case, you have to be able to show that what you're talking about is reasonable. So in the validation, how do we know there's that much water in the cloud? Okay, the properties of water demand that the temperature at 26 miles altitude, the water and density pressure is given by the sublimation curve. Now you remember that we put the curve up there and we showed that there are specific temperatures and pressures where water will transition between states. Those are not guesses. Get this. That is measured, precise quantities. If you are a fraction, a tiny little bit on one side of that line, that's where you're going to be. If you are a little bit lower pressure at a given temperature than the sublimation line, you've got vapor, period, the end. That's the way it is. If you want to get the solid on the sublimation side, if you want to get deposition, you have to have temperature and pressure such that water will actually form into that state. Remember, the properties of water, which is dependent on the fact that it's a dipolar molecule and it's got these characteristics, all of that is what determines these things. And water isn't changing capriciously. It is water. The water molecule is very precise in how it behaves. And so we can see that there is an exclusion line which Dr. McDonald talks about. And he says, above this line, you can't get a cloud because the temperature is too high. Remember, in the stratosphere, the temperature is going up and the pressure is going down. As you go up in altitude, the pressure goes down and the temperature goes up. And you get to a point where you cannot get a cloud to form, period, the end. It won't do it. This was barely... That cloud was barely in the region where a cloud would form. All right, which is another thing that makes you think, oh yeah, that's water. Sure. God put the cloud up there. I'm going to say that with boldness. God put the cloud up there. And he put it in such a place and with such a size that man would never get credit for it. Now... All right, the same conditions of partial pressure and temperature exist in a lower part of the atmosphere. That's if you take the Brother Malachi, let's go back to that saturation curve. Or no, excuse me. Go back to where am I? Slide 20. Let's go back to slide 20 and review. All right, so here you have the pressure curve and the temperature profile. And the temperature profile, as you go up in the troposphere, originally, as you go up in the troposphere region, the temperature is going down. The pressure is going down, but there's a point there where the vapor pressure of air, or the water, the vapor, the partial pressure of the water, is going to be at this 2.2 millibar at a temperature of about minus 18 or minus 20 degrees Celsius. Some in that ballpark. That's about what the temperature would be up there. And in that, in the troposphere, when those conditions are met, cirrus clouds form. The reason the cirrus cloud forms is because that's colder than ice. It's going to form ice. And a cirrus cloud is an ice cloud. And it forms a hexagonal, it's the 1H type of ice. There's 11 different types of ice, or more. But this is the one that forms right on the line, which is the hexagonal form. If you compress it a little more, it goes to the cubic form. If you, well, anyway, all right, I studied all that too. So, if you find the point in the troposphere where those conditions are met, you'll get a cirrus cloud. And so, if you meet the same conditions, I don't care where it is, it's going to form a cirrus cloud, because that's what water does. It can't do anything else. So, the point now, let's go back to our 33. You form a cirrus cloud. So, if the cloud is like, if it looks the same as a cloud, a cirrus cloud, only it's too high, it's way, way higher to be naturally formed, then that's what it is. It looks like it, it's got the same properties, it's got the right conditions, that's what it is. Okay? Now, a cloud cannot form, again in our validation, we know that if you go higher in altitude, the pressure goes down, so it'll go to vapor. And also, if you go up, the temperature will go up. So you remember, in the stratosphere, the temperature was going up as the pressure was going down. So you're going to reach a point where clouds won't form. All right, next slide. There is a possibility of polar noctilucent clouds to form. Because as you get above where the temperature changes and it starts going back down again, that's from the top of the stratosphere to the top of the mesosphere. And the mesosphere, the pressures are getting lower and lower and lower all the time. But way up at the top of the mesosphere, at about an altitude of 50 miles or 80 kilometers, it actually gets cold enough to where clouds can start forming again. That's 50 miles up. And this cloud was never seen at 50 miles. In fact, probably nobody would have noticed it at all. Those clouds form all the time. That's not strange. All right. Now, according to government publications, the Air Force Geophysics Laboratory, I downloaded their publication, and this is where you get the standard tables for atmospheric conditions or constituents. All of the different things, and they cover everything. It's like a whole bunch of stuff that we don't need to talk about. But the ones that we do want to talk about are water vapor, nitrogen, oxygen, argon, the three main constituents, plus the water vapor, plus all the other stuff. But they give nitrous oxide and methane and all of this. And what you find is that water vapor starts off at a fairly high concentration down at the low pressures and low altitudes, because it's possible for water, as you raise the temperature, you can have more water in the air. So you can have as much as 1% of the atmosphere could be water vapor down here where we live. And if it gets to saturation, then you'll be in a cloud. How many of you would love to live in a cloud? Kids, won't it be wonderful to live in a cloud? Ever been in the fog? You can't see. You run into stuff. That's living in a cloud. So anyway, as you go up, the temperature goes what? As you go up in altitude, the temperature goes down. And so you rapidly run into this transition between the temperatures and pressures where water will condense. So you take the vapor, the quantity of water, and it gets higher, and it reaches a point where it gets cool enough that now it'll condense. It'll start forming a cloud. And so the water condenses. That means the vapor pressure of the water now goes down and matches the saturation curve. And as you keep going up in altitude, you'll get colder and colder and colder, and the vapor pressure of the water keeps going down, 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 until finally you reach a minimum vapor pressure of the water and a minimum quantity of the water, because the water has all condensed out. And so the amount of water that you have in the stratosphere by natural means is 5 parts per million by volume. 5 parts per million. Take 1 million particles, and 5 of them are a water molecule. Okay? The nitrogen is still 78%. The oxygen is still 21%. The argon is still 0.9%. Everything else is still in that 0.1%. The water is down to 5 parts per million. As you go up towards the top of the stratosphere, the water content actually goes up a little bit. It goes to 6 parts per million. Now, why does it go to 6 parts per million? Because the methane reacts with the ozone and actually creates some more water. The little trace amounts of methane that are in the atmosphere up there that are mixed in, and the ozone, remember that's the ozone layer, and the ozone layer, the reason the temperature goes up is because of the ozone. It's absorbing energy. So now, we see this is the way water behaves. So, the natural concentration of water vapor in the upper troposphere is around 6 parts per billion. It's million. 6 parts per million. I corrected it. Okay, I got it right. So the water concentration that's required to make the cloud is 100,000 times more dense than that. And what that's telling you is, telling me, telling all of us, is that a cloud will not naturally form in the stratosphere. It simply won't do it. But if you could somehow put the water up there, then you can make a cloud. And the amount of water that would have to be up there from the natural amounts that would normally be there is 100,000 times more dense. So basically, whatever made that cloud, it was deliberately put there. It was not an accident. It was not an act of nature. All right? Now, the next slide, I showed these last week, but I want to spend a little bit more time on them. 35. Now, I did this calculation based on the vapor pressure of the water that's naturally in the atmosphere to show you how far away we are from making a cloud versus the natural things. This curve is the temperature curve on the right, and the curve on the left is the saturation temperature curve of the water as it actually exists by concentration. So we start off following the pretty closely. You can see that the temperature versus the saturation temperature curve follows closely in the troposphere. But when you get to the top and the temperature turns, the water concentration gets wrung out, and it doesn't have much water up there. So when you calculate what the saturation temperature would be for the given vapor pressure of the water, that's the temperature that would result. And so from the top of the troposphere and the bottom of the stratosphere up to the top of the stratosphere, you are orders of magnitude. You are way, way different in the temperature. So you're so far away from making any kind of condensation because you're way over here in this vapor space. The way water acts. Next slide. Here's the same curve, only it's now with respect to pressure. So if you take the temperature, the normal temperature of the water, the actual vapor pressure versus what the vapor pressure would be if it was at that temperature. And so you compare the pressures, and you can see that we're off by 1, 2, 3, 5 orders of magnitude. That's the factor of 100,000. So when you compare the actual result, what's normally there, to what's required to make a cloud, you can see how far away you are. The natural amount of cloud, or the natural pressures from the natural amount of water you have up there, it won't make a cloud in the stratosphere. We said that, but this is validating that through the mathematics of actually just computing where you are on the saturation line. I had to write a little program to make that happen, but that's it. All right. Now the next picture we've already seen, but I want to talk about it just a few minutes. Here's the cloud. This was taken, remember we read from the article that said just a few minutes these things dissipate. This is taken 5 minutes after liftoff. And it's a 10-second exposure. And the reason you'll see the horizon looks like it's getting brighter, this is actually at sunrise. So this was a pre-dawn launch. And so the sun lights up, and now we've got something that's illuminated up in the upper atmosphere from the sun. But you'll notice the way that this plume is dissipating. The winds are blowing, and they're blowing at different velocities at different elevations as you go up. The actual curve would be from the very bottom where you start, and just make a smooth curve going up to that top, and then you'll see that the cloud is actually being pushed around. And the cloud is being pushed around more at the interface line between, or up in the troposphere, upper troposphere. That's where the jet stream is. That's where all the high velocity stuff is. And you see that same thing in that cloud plume as it's being pushed around. And you notice that there's no plume above a certain altitude. That's because water can't condense above that atmosphere, that altitude. And so then 5 minutes later, okay, let's go to the next go to 39. There we go. Here's what it is 40 minutes after launch. The lower part of the plume is gone. It's already dissipated. And then what you see here is these different layers. The brown right there is stuff that's still not quite been illuminated by the sun coming up. But you can see it's going in all these different directions and all these different pushes and different things. That's because the plume is falling. So there's nothing to suspend the water up there, because it's a high altitude, and once it gets at this high altitude and forms a cloud, it's now heavier than air, and it begins to fall. All right? 40 minutes. What do you think it looks like 2 hours from this? 2 hours from this, it's all gone. It's completely dissipated. And that from a rocket, a space shuttle, that's 2 orders of magnitude larger than the thrust-augmented Thor. 60 times larger. So you're telling me that a rocket that's 1/60th of that is going to form a cloud that's 30 miles across and 50 miles deep? I'm not the insane one here. I'm not the one making stuff up. You're making stuff up if you think that's got a connection. And if you tell people that that cloud was formed by the thrust-augmented Thor rocket, you're lying to them. You've never done the math. You never proved it. You never did a root cause. You never validated your assumptions. Dr. McDonald did. And he never said that cloud was caused by that rocket, though he wanted it to be so. He desperately wanted it to be so. But he had enough integrity to be able to say, I don't know. And he did. He said, I don't know. He used some words in here. When I read this, this is from WeatherWise article. He says, if this was, in fact, the aftermath of the Thor explosion, persistence of a circulation and of condensate for nearly 4 hours of downwind drift will be of considerable meteorological interest. I read those words and I thought, no kidding. This is an academic, a scientist, who is writing words that he's not allowed to say it would be a miracle. He can't say that in a journal, so he has to say that. Then he says, if it was not due to the explosion, then the mystery will be back where it started at sunset on 28th of February. And in fact, that's where we are today. Further validation comes from, let's go to my last slide, this is slide 41. This is it. We're going to stop right here. There have been hundreds and hundreds of Soyuz launches from the Baikonur Cosmodrome in Russia and maybe other places, but there have been 1,800 Soyuz rockets. In fact, if people want to get to the space shuttle, to the International Space Station right now, if you want to do it today, you have to take a Soyuz rocket. So the Soyuz is powered from, RP-1 is just glorified kerosene. It's a specially refined kerosene. And it's similar to the material that's used, the same propellant that was used in the Thor rocket. So the exhaust of that is mostly carbon dioxide and water. And the exhaust plume of every single Soyuz launch is fully dissipated in 2 hours. And it's bigger. And that's, what I'm saying is, what we should all come to the conclusion is that this cloud could not have been due to the launch of the Thor rocket on February 28th, 1963, at just before 2 p.m. local time. Not possible. If you're going to say it is possible, you better have your physics lined up. Root cause won't allow you to make that statement. Of course, if you don't care about root cause, then you can say anything you want. But it also make you a liar. I've been on dozens of root cause teams. I have been on places, I've been on root cause investigations that were just sort of this similar thing, where somebody made a connection. And it sounded plausible until you buried down into the depth of it and you realize it had no foundation. And if you're not paying attention, you'll wind up with root causes that don't address the actual root cause. They might sound like good ideas, but here's what happens. If you spend your time and your energy solving a problem that doesn't exist or solving the wrong problem, you've just wasted a lot of money and you haven't kept the thing from happening again. So root cause is really, really important, especially when you work in an industry where any kind of an incident or action winds up on the front page of the newspaper. Whether it's got any, significance safety-wise or not, it doesn't matter. How many people are afraid to fly? That's okay. It really is. It's perfectly fine. If you were flying with me, you might really have a good reason to be afraid to fly. I actually haven't exercised my pilot's license in probably 20 years now. But I do have a pilot's license, and I was trained, and all of my landings were successful. But here's the deal. The reason people are afraid to fly is because of perception. You are actually safer flying than you are driving to the airport. Now that might sound strange, but the fact is the actual documented safety record of the commercial airline industry is tremendously, it's really, really good. It wasn't that way to start with. But it got that way because every single accident gets a root cause investigation. And in that root cause investigation, they go find out what was the thing that went bad. What was the thing? What can we fix to make sure this doesn't happen again? And the NTSB will put out orders that say, all right, here's the problem, fix it. And the manufacturers that go in, they'll fix the problem. And that problem won't happen again. And if you find where the manufacturer did not fix the problem, then it's possible you'll get another accident and people will be killed. And so root cause is extremely important. And when you're talking about the lives of people, the pilot holds the lives of the people in his hand. Not just his, but he's responsible for everybody on board. He is accountable legally, and he's accountable before God. And if you are going to tell people that some event happened because of some tenuous idea that you may have, because it fits your particular agenda or fits your particular point of view, you'd be guilty of lying to people, and the people you took with you are your responsibility. God will hold accountable what the preacher tells the people. God will hold you accountable for telling the truth. If you don't feel that accountability, there's something wrong with your calling. One of the scariest things for me, one of the most frightening things when I looked at what Brother Branham said about what a minister was responsible for. If anybody really had the weight of what that called for, you would run from the pulpit. You would never want to get out there and try to lead people, lead them in the ways of God. You better know what you're talking about, and you better have actually had the experience with God. As the prophet told us, no man has a right to stand behind this pulpit until he's met God face to face. And there's, you don't have to go very far to find pulpits where that's not true. But I wear these things. I studied in Ezekiel just as a word of warning. Ezekiel chapter 14. Ezekiel chapter 14. Certain elders of Israel came to me and sat before me. The word of the Lord came to me, saying, Son of man, these men have set up idols in their heart, have put the stumbling block of their iniquity before their face. Should I be inquired at all by them? Therefore speak unto them, and say unto them, Thus saith the Lord God, Every man of the house of Israel that setteth up his idols in his heart, and putteth a stumbling block of his iniquity before his face, and cometh to the prophet, I, the Lord, will answer him that cometh according to the multitude of his idols. You want to get a straight answer from God? Get your heart right first. Don't come to God trying to tell him what you think. You won't get a straight answer. In fact, the answer that you get is likely for you to be even more deceived than you were before you started. Jesus told the disciples and the people in his day, he had followers, and he had too many followers. And he said things that they could not understand. Whoa, what's this? And they walked away, and he never tried to stop them. So don't think that God is obligated to you or me. He's not. He is obligated to his word. His own integrity demands that he be obligated to his word. Now, these people that go off trying to prove things wrong and nitpick and find errors are the same class of people that put Jesus on the cross because he didn't agree with their doctrine. Brother Luke, dead on the money. Dead on the money this morning. Now, praise the Lord. I wish I had a more upbeat note. Thank God for his mercy and his grace. Amen. If you do come with a right heart, if you do come seeking God with a true and pure heart, he will not turn you down. He that cometh to me, I will in no wise cast out. Thank God for those promises. Amen. Let us stand. Amen.